Welcome to my OpenCV course using Python. In this course, we're not only going to implement the code in Python, but we're also going to spend a lot of time focusing on the theory. That way, when something breaks or doesn't work, you know exactly why it doesn't. We will start off with the basics of image processing. We will begin by going over how to install OpenCV using VS Code, go into reading and writing images and videos, talk about different color spaces like RGB, Grayscale, and HSV. Then we'll dive into histograms, go into filtering, and finally thresholding. Then we'll move into more advanced topics. We're going to go into things like edge detection, line detection, feature detection like corners and SIFT, object tracking, camera calibration, and post estimation. So by the end of this course, you should have a solid understanding of computer vision and be ready to tackle real-world problems. All right, let's get started. If you're new to my channel, I have a website at kevinwithrobotics.com where I have a bunch of resources on robotics and computer vision. So check it out and subscribe to learn more. Okay, so to install OpenCV, you would use this command right here, pip install opencv-python. And to find the command, you could Google search pip install OpenCV and you'll find this link here that will tell you the command that you need, okay? And to set up your virtual environment, you would run the first command right here, python-mvenv, and then this is the name of your virtual environment. I just call it OpenCV-env. And then to activate it, you run this line of code right here to activate. Okay, so here we're gonna have a demo program. And notice right here, you could see this. This is how you know your virtual environment is up and running. So here we're gonna create a quick program to make sure that our OpenCV was installed correctly. So I'm going to go ahead and type import CV2 as CV and then do a if name equals main and print CV dot version. So if I run this, you see that my version is printed out. So that means my OpenCV program is up and running, okay? So if you found this video helpful, give a like and subscribe, and I'll see you in the next one. All right, so in this video, I'm going to be giving an introduction to what images are. So I'll be talking about what an image is, go into some of the pixel ranges you should expect for an image, talk about the RGB for a pixel that you look at for an image, and then talk about some of the dimensions for an image as well as some tricky aspects to some of the dimensions. So stay till the end to see what that's all about. Okay, so what is an image? So when you get an image like this cute cat that I have right here, what's really happening is you have a matrix that has a bunch of numbers. So we'll talk about what some of these numbers mean, but for now, just know that images are represented by a bunch of numbers stored inside a matrix. Okay, so when dealing with these numbers inside your matrix, we want to look at what the pixel ranges are. So typically you'll hear what's called the 8-bit representation. And the reason why it's called 8 bits is because when you do 2 to the 8, you get 256. And what that tells you is that the minimum number you could guess is 0 and the maximum is 255. So 0 to 255, you get a total of 256 numbers. And 0 will usually correspond to black, and the highest value will correspond to white. So that's how you actually use the numbers. And sometimes you might see the range might be shifted so that the middle is actually half of 255. So depending on what convention, you may see different representation for your pixel values. Okay, so now we have the BGR for pixel. So what that is when you have a pixel value, right? So typically for 1 pixel, you're going to have 3 numbers. And depending on the combination of these 3 numbers, you will have different colors that represent it. So depending on which program you're using. So in this case, if we're looking at OpenCV, the order is like this, BGR. Sometimes you'll see it as RGB. So depending on what you're using, you'll have different conventions. But pretty much every single pixel can be represented by a combination of these 3 numbers. And as we said earlier, the ranges of these numbers will be between 0 and 255. So now we want to talk about image dimension. So usually we have a single pixel, so sometimes a single pixel might be just, one of the values. If you're in the z direction, you have in the z you have 0, 1, 2, so you get three channels, and then you have m and n. So the m is the height and the n is the width of your image. So one thing that's tricky is that, usually you have your axis here, right? This is actually your x, and this is your y. So notice that your x corresponds to your n, which is your width, and then your y corresponds to your m. So it's kind of flipped in a way, but the best way to check, I would say, is if you mess up, just switch it to see if you got it right. And if you got it wrong the third time, it's okay, no one will know. But just keep trying until the direction is what you expect. And that's a good thing about programming is that, if you mess up, you get immediate feedback when you try something new. Okay, so pay attention to this XY. So if you found this video helpful, give a like and subscribe, and I'll see you in the next one. Okay, so in this video, I'm going to talk about reading and writing images. So I'm going to talk about what is reading and writing images, why do we need it, how does it happen, and we'll jump into some coding examples. Okay, so what is reading and writing images? So when you have a photo here, you have some location in your PC, some folder, you may want to extract that image, or you may want to write that image. So that's basically the idea of reading and writing images. Okay, so why do we need to read and write images? So when we read and write images, usually the main thing is we want to interpret the image to do some sort of image processing on it. So right here is an example of me trying to find some of the years here with some basic uh, type of segmentation type of method. And then other times you may want to write images for saving. So maybe you have some things for analysis that you're doing, or maybe for pre-processing. Okay, so depending on what stage of the image processing pipeline you're at, you may need to do different actions with your images, whether it's reading or writing. Okay, so how do images get read and written? Okay, so we briefly talked about it before, but basically you have a matrix that gets read. So when you have a picture of this cat here, we're going to see a matrix when we read it. And likewise, when we write it, we're going to pass back some matrix that we see. Yeah, maybe the new matrix we're passing back could be the same or maybe modified. Maybe there's parts of the pixels that you're changing. Maybe you want to black it out and you make all of these to 0, for example. So you may do some sort of modification to the matrix that you have. Okay, so let's go ahead and jump into some code. So let's have an example of here on how to read an image. So let's go ahead and make a function called readImage. Okay, so I will be calling it in here. So first off is I need to, I have my image stored in demos images. So gonna get my main directory. I'm gonna call it root and get my directory here. Okay, so that's getting my directory and then my path of my image. And the reason why I'm doing this is because I like to organize my files into folders instead of just putting everything in one. So that's why I'm doing this step. But if you have your file directly in your main folder, you don't need to do this. Okay, so this is just something that I prefer. And then this is my folder called demo images. And then I'm going to call this qpic1.jpg. Okay, so that is how I could set up my path. And then the next command here is I'm going to call my image img, and I'm going to read in the image and pass in the path. So the path is going to be a string. So once I do that, to view it, you could do cv.show, and you need to pass in the name of your image and the image, which is this is going to actually be a matrix here. So for a 3D image or image with color, you have m by n by 3, and then if it's grayscale, it's going to be by 1. Okay, so with CV, typically you need to do a wait key. So and you have a delay of 0, which means for infinity. So I could hover over this and you could see some of the documentation, but that's basically what it does. So when I run this, we should see an image pop up, which is my cute little kitty here. So now I can go ahead and close it. Okay, so for the next part, we'll take a look at some of the ways you could view this matrix. Okay, so I'm gonna put a breakpoint here. I'll just call this debug equals 1, so I know I'm breaking here. And then if I do debug Python file, we want to take a look at this image. So if I scroll here, we could see some of the properties of this. Let me just move this stuff down. So notice here that this image here, if I hover over it, you can see all this data, right? If I go to my debug console, if I try typing image, I can see all this data, right? But this is not really a good way to look at this data. Here you can also see the shape of this image, which is 985 by 1170 by 3. The way I like to view this image is to view value in data viewer. Okay, so what this does is it'll actually display all this data into like a Excel type of table format. Okay, so this may take a while to load up for the first time, so we'll go ahead and let it load for a bit. So notice here that it tells you variables with over 1,000 column may take a long time. So that's the warning that it tells you, right? So here I could specify, let's say I wanted to view the first channel. I could hit apply, and there you go. You can see this is a nice way to view all the numbers of your image. So you can see that these here are very high numbers, close to 255, which means that it's probably the background, which is close to white. And if I scroll down, these low numbers are dark because it's like the fur area, which is dark, and black, which is low numbers. Okay, so now we'll go over an example of how to write the image. So to write an image to your folder, I'm going to make a function here called write image. And again, I will have some path. So I'm going to copy this part, which will be identical. So no point in rewriting that. And then you might want to specify your output path here. So I'm going to call this out path. And my output path, for example, I could call it this. And maybe I'll name it output. Then if I do cv dot write, and then put output path. So output path is going to be the path of your output, and then the next argument is the matrix that you're passing in, which will be the image. So if I write this and do call write image, so if I run this and I check my demo images folder here, we will see that there's an output. And that's the picture of the cat. Okay, so that has confirmed that our writing is successful. So if you found this video helpful, give a like and subscribe, and I'll see you in the next one. All right, so in this video, we will be talking about reading and writing videos using OpenCV with Python. So first, I'll talk about what is reading and writing videos, why do we need to read and write videos, how do videos get read and written, and we'll go into some coding examples. The first one is read video from webcam, and then read video from file, and then write video to file. Okay, so what is reading and writing videos? So typically when you have a video, it's going to consist of a bunch of frames, and each frame you could treat it as an image. So here you can see we have 3 frames. And when we're reading and writing it, we're essentially getting these frames, sending it back and forth between our folder. Okay, so why do we need to read and write videos? So most of the time you will want to do that is because you might want to interpret something in the video. So here is an example. Maybe you have a self-driving car and you want to identify the different things you see in the scene as your car is moving along. So you might identify a person or another car and so on. And then you may want to save the video for pre-processing or analysis of the videos that you saved. Okay, so how do videos get read and written? So typically what happens is, as we saw in the first one of the earlier slides, is 3 frames. So you could think of each frame as they have the 3 channels, and each channel will have their own color. So here you can see we have a set of 3, a set of 3, a set of 3, because each image has their own channels. So we're passing back the matrices back and forth, and each time we get a frame, we're going to have m by n by 3 dimension for your matrix. Okay, so that's how we're passing back and forth the data. Okay, now without further ado, let's jump into the coding. We're going to call our first function video from webcam, and you get to see my lovely studio. So here what we're going to do is, for anything, let's have our if name equals main, and we're going to call our video from webcam. Okay, so inside here, the first thing we want to call is create a video capture object, and we're going to save it into cap. So we just have CV and then video capture, and then this number 2 here will specify the camera that you have. So here I have 3 cameras. It's going to be a third one is 0 index. So that's why I'm using 2. You could kind of play around with the numbers to see which one is the correct one that you're supposed to be using. So just test it out. And I'm going to say if not cap dot is opened to do some check, and I'm going to exit. So that's just a safety in case the webcam is being hogged by another program, then we know to, you know, not keep trying. And in that case, you might have to debug your program. Okay, so I'm gonna have a infinite loop here that will keep reading the frames from my video camera. So gonna return frame. The cap read function, what it does is it returns a return value to see if it's true or not, and then the frame is the each image. Okay, and then I'm gonna do a quick check to see if it's true, meaning that everything is working. I'm gonna display my webcam feed by passing in the frame. So the frame is m by n by 3 if it's color. So that's my webcam feed. And then I'm going to add in a break key because I need a way to terminate when I'm done. So I'm going to say if cv dot wait key and then pass in 1. So I'm going to wait 1 millisecond and check if I press the Q key. So if I press the Q key, then it will break, and thus it will terminate my program. And then I could do a cap dot release and have a cv dot destroy all windows to close my window. Okay, so this should allow me to read my webcam. So if I run this, we should see a window pop up. Okay, so now you can see my camera's showing. I actually ended up changing it to 1 because my other webcam wasn't working properly. But here you can see that my studio is back here. It's all green. It's my green screen. But yeah, so that's how you read a video from webcam. Okay, so now we're gonna do a read video from file. So it's gonna be kind of similar, but just a little bit different. Go ahead and show you how that looks like. So we'll call this video from file, and then we'll call it here video from file, comment this line out. And then inside of here, what we want is read in our file. So we have os.getcwd to get our root folder, and then our video path is going to be os.path.join, pass in root, and then it's in my demo images folder, and I called it cute video 1.mov. Okay, and again, we're going to create our cap object called CV, and in this case, video capture, what we want to pass in instead of a number is going to be the actual path to our video. Okay, so once we have that, we're gonna do a while cap dot is opened. We're gonna again retrieve it, do a cap dot read. So we'll read each frame at a time, and then we'll do cv dot show, pass in video, and then my frame. Then I'm gonna add a little bit of delay here You're gonna have 1000 divided by 60. This is something you could kind of play around with. Here we're assuming we have 1000 milliseconds divided by 60, so that's the units. But you could kind of play around to see what works. Because sometimes when you read it, it's kind of choppy, too fast or too slow, depending on how it's actually interpreting your data. So you might have to play around with that and see what looks good. Okay, so we're gonna add a wait key again. And this is if we need to break. So we'll have check for our Q key. And if we press our Q key, then it'll break. Okay. And we need a double equal sign here. So let's go ahead and see how this looks. If I run my Python, of course, we need to add in our colon here. So if I go ahead and run this, we see our little kitty being licked by another kitty. Okay, so that's the video that was in my folder. Okay, so let's see. Okay, so now what we want to do is write our video to file. So let's go ahead and make a function for that. Call it def write video to file. And then we're going to call this write video to file. Okay, so that's our function. And inside, we're going to go ahead and we'll use some of this stuff here. So we had our video from webcam, right? So here we want to read it instead. So we have our cap, and then some additional things we need to create is our 4cc. So this is our how we have like a it's like the compression format of how your video is stored. So we have a cv dot video writer object now, and then 4cc. So usually you have to pass in like a 4-letter code here. Here we're using a xv id. You want to put it in quotes here. So this is a type of MPEG-4 encoding. There's different ones you could choose, but this has been pretty robust in my experience. So you could do root equals os dot get cwd again for my path. And in this case, I want my output path to be os dot path dot join, and then what we want to join is root, and then my output folder, I'm just going to put in my demo images and call this webcam dot avi. And this avi format is just something that I tested and I know works well, but you could go ahead and try other formats as you please. So here we're going to create a out cv dot video writer. So we're going to pass in the output path, which will be a string, and then a 4cc object here. And then we have 20, which is the frames per second in float. And then the frame size, I'm going to do a 640 by 480 just to make it small. Okay, and then we have, let's see, we're going to have a while loop. So here we're going to say instead while cap is open. And again, we're going to read it, get the return value and the frame. And then if it's true, we're going to do some stuff. So here we could still show it, but now we want to write it. So we have our out object here, video writer object. So we're going to do out.write and then pass in the frame. And then once we're done, we'll hit the Q key to exit. And then we could do a cap.release and an out.release. Okay, so if I run this, my face should show up again, and then it should start recording. Okay, so it might take a minute for the webcam to initialize. If I go ahead and run this, okay, this was pretty fast. You can see that I popped up, hello, and then I'm gonna stop it by hitting the Q key. So once I hit the Q key, I should see this webcam.avi stored. So in my demo images, I have a webcam.avi here. Okay, so now if I open up my file, there was some error just then, but I fixed it. But now you can see that my video is playing. Okay, so that's how you would write a video to your file. So if you found this video helpful, give a like and subscribe, and I'll see you in the next one. Alright, so in this video, we're going to talk about reading and writing pixels using OpenCV and Python. So we're going to talk about what is reading and writing pixels. What do we mean exactly when we say that? We're going to talk about why we need to read and write pixels. We're going to talk about how do pixels get read and written. And then we'll go into some coding examples, reading and writing single pixel values, and then reading and writing regions of your image. Okay, so that will be the more interesting one. Okay, so what is reading and writing pixels? So usually when you have an image, there's going to be some region or a single pixel you're interested in, but most of the time it's going to be a region. So you may be interested in looking at this area and you want to see, what's going on in this area. So to know what's going on in this area, we need to examine the pixel values, and then we'll talk about how we actually look at that. But if you recall from the previous videos, we mentioned that we have a RGB channel. So even though here we see an image, there's actually 3 layers of data behind this. Okay, so why do we need to read and write pixels? So the main reason why you want to do that is you may want to interpret parts of the image. So like we mentioned earlier, you have your RPG channel. So maybe here we want to see maybe the texture of the fur or maybe the breed of the cat. So you might want to examine the hair patterns, for example, or maybe it's the eyes you're interested in. So there might be different parts of the image you're interested in. And then maybe you want to save it for analysis later, maybe some post processing to see if this kitty has been good, maybe by looking at the expressions or something of that nature. Okay, so when we actually look at the region, what we're actually looking at is the pixel values. Okay, so here we have 3 layers, and all of these 3 layers represent the BGR channels if we're looking at OpenCV. So when we access these values, we could see the actual pixels value that corresponds to this region. Okay, so that will give us some information. And then if we wanted to do any post-processing, we could probably modify these values. Maybe they go to 0 or whatever you want to do with the values. Maybe you want to convolve it with a filter, which is a concept we'll talk about later on. But pretty much once you get the matrices that represent the numbers, you could do anything you want with it. Okay, so now it's coding time and let's jump right into it. Okay, so we're gonna have our usual imports right here, and we're gonna call our functions. So we're gonna first look at read and write a single pixel. So def read and write single pixel, and we're gonna call our function in here. So inside, what we're gonna do is use our usual image that we've been using. So roots is os.get the path, and then the image path is gonna be os.path.join. Gonna pass in roots, and then our folder was demo images, and I called it cubepic1.jpg. So we're gonna read in the file. So image is cv.read and pass in the image path. And then from there, we want to actually convert it to the BGR to RGB because we're gonna do some plotting with the matplotlib, and the matplotlib actually takes RGB. So we're gonna do some quick flipping with the channels. So we're gonna do cv.cvt color and then pass in the image, and then the integer will be the color code conversion. So color color we do BGR to RGB. So we're gonna do plt.figure and then plt.show. And the reason I'm using this is because with the cursor, we get to actually see the values of the pixels. So that's pretty nice. So when I run this, you'll see a window pop up with the cat. So notice when I hover my cursor, you can see the values at the bottom, which corresponds to the pixel values. But this is very useful if I want to, access a specific pixel value. So If I want to go somewhere in the eye, I could choose some number, then I could see the exact pixel for the eye. Okay, so I could try doing that here. If I were to say eye pixel, and let's just choose a number that was near the eye. So we're gonna access the pixel by saying 312 by 350. So this will allow me to read the value. So if I debug here 1, we could see what the value is. We'll see how that value is being stored here. So notice that iPixel is going to be an ND array with 3 values. Okay, so here I'm specifying 2 values, and then it's going to return me the actual RGB values. Okay, and again, it's RGB is because we've inverted or switched the channels here. Okay, so now maybe we want to modify it or write a value to the iPixel. So what we could do is access the values here, so 350, and maybe we want to make this value, what do you guys think this color is? So 25 is bright in the R channel, so it's going to be red. So if I plot this new one, I'm going to do a before and after plot. So if I plot this now and run it, we should see the first image is the same, but the second image, if I zoom into the eye, we should see a red speck. Okay, so this red speck is because we modified the pixel value of the eye. Okay, so now what we want to do is access a region of the image. Okay, so we're going to go ahead and make a new function for that and call it, what do you guys think it's going to be called? Read and write pixel region. Okay, so this be our function name. I'm going to comment this out and then call our region function here. And then we're going to do some of the similar stuff like we did, which is reading this goodie. And then now we read the image. I'm going to use the same plotting, so we could plot the image here. And then now we actually want to do something interesting. So we want to extract the eye region. So if we take a look at our image, and again, this is why I like the IM show from PLT. We could see the eye region is roughly from here to here. So notice the upper corner is like 302 to 270-ish. Bottom-ish is like 390, 352. So I actually have these values down already. So we're going to do I region equals IMG RGB. And then to access a region, we could do 290 to 340 and then 326 to 380. Okay, so again, this part could be confusing sometimes if you mix your X and Y, because here we're actually accessing the rows and then the columns. So this is actually the Y and then the X. So if you just do one way and it's wrong, just try flipping it. Okay, so that's the best way. So that's my eye region, right? And I can actually see my eye region. If I were to put a debug here as before, or similar to what we did, put a breakpoint and run this, we'll see what the eye region variable is here. We can see it's an ND array, and you can see that I can also view it using the view value and data viewer. So this will show me all the pixels inside this region. So we could see that we could slice this data here, and if we want to just look at one of the channels, say the first channel, I could apply this. Then this gives me a nice view of the data. Okay. So I'm going to go back here. Now, perhaps you want to write some value. So here, what I want to do is I have some region. So maybe I want to copy the eye somewhere. Okay. So I'm just going to do something funky. So I could do dx equals 340 minus 290. So that's going to be my region. And then I have dy equals 380 minus 326. and then I'm gonna have a start X. So that's just the area that I'm choosing. I'm actually gonna put it somewhere on the forehead, and then I'm gonna put 238. This is the start location, and then the start Y is gonna be I have set at 411. So I could do IMG RGB, and then I could specify some locations, start X to DX, and then I could have start Y to start Y plus DY, and I could set that to the I region. Okay, so if I were to plot this new image, what I'm actually doing is copying and pasting the eye to the forehead. So this will be a three-eyed kitty. Okay, so if I close this and if I zoom in, you could see that this cat now has three eyes. Okay, so a little bit creepy, but yeah, seems like it's working. Okay, so that's how you read and write regions of pixels. So if you found this video helpful, give a like and subscribe, and I'll see you in the next one. All right, so in this video, we're going to talk about RGB color channels. So we're going to first talk about what is RGB color channels, why we need RGB color channels, how do we use RGB color channels, and then jump into some coding examples, talk about some pure colors, gray channels for the BGR colors, and then the actual BGR color channels to see colors for the individual channels. Okay, so what is RGB color channels? So when you have an image, you'll have three channels usually. So here we have the blue one, the green one, and the red one. But with OpenCV, you actually have BGR instead. So the order is flipped, and depending on which program you're using, you may have different channel order conventions. But usually these channels you could there's a simple way to switch the different order of the channel with a simple command. Okay, so why do you need RGB color channels? So the different color will usually give you different information, and later when we talk about some HSV color channels, we'll see a very nice way to segment it. So segmentation is a pretty common thing that we'll need for colors, or like in this example here, when you do green screen, like right now, I actually have a green screen behind me and it's doing some basic color segmentation. So the reason people use green is because it's not a very common color in most people's skin tone, hair, or clothing. So they use that to easily segment out the background. Okay, so how do you use RGB channels? So when you have a picture like this and it gets converted into the three color channels, you'll have a matrix that has a depth of three. So the three layers is the depth of three. And we could actually use the individual layers. So each one is going to be a 2D array. And we could take that 2D array and do different things with it. We could convert it to grayscale, like we'll talk about later on, or you could look at the individual channels. Maybe there's like a histogram plot or something you could use to see the actual channels by itself, one by one. Okay, so now it's time for coding, and we'll jump right into it. Okay, so we'll start off by doing some coding with pure colors so we can see how solid colors can be formed. So we can call this pure colors. Okay, so I'm gonna go ahead and create some zeros. So I'm gonna make a matrix of zeros, and maybe the size is gonna be 100 by 100. And I will also make some ones. So we're gonna see later on that we're gonna add these values and then multiply it to get pretty much zeros will be black, and then the highest, I'll take my ones, multiply by 255 to get the highest value, and then do different things with it. So with my blue image, I could use cv.merge. Merge is a function that will combine the different 2D arrays. So here I may have 255 times ones. And then the other channels, I'll have zeros. That will show that the blue channel is just blue. So if I do plt.figure and then plt.subplots, I'm gonna have a couple of different plots later on. So I'm gonna do a 2 by 3 and then plot it in the first one. And then here I'm gonna do plt.show and plot the blue image. So here I have my blue channel, my blue image, and then I could do my plt.show. Okay, so if I run this, maybe you want to add a title, and here I'm going to call my pure colors. So if I run this, we notice that it's actually red, right? So what's happening is when you actually use the show, the order will be different because with CV show, it'll show BGR, and then with this, it'll show RGB, right? So that's why with this, it's actually going to be for the red channel. So if we want BGR blue channel, then we're going to actually have zeros, and then here we're going to have ones. So 255 times ones. And now if I run this, we should see a blue channel, okay? So that's good. And the reason why is because matplotlib's show uses BGR, and then OpenCV's will use uh, the RG. The OpenCV will use BGR, and the matplotlib will use RGB. So that's why the blue channel is in the third dimension, okay? So now, if we keep going, we'll see the other stuff. So here we have, so if we want to be consistent, we could use it. But the reason I'm using the matplotlib is because I'm using the subplot function. So CV doesn't have subplot, so it makes it a little bit easier. Okay, so if I replicate this, and maybe now I want to see, so our next channel might be G. Well, here we just RGB, so we did B, and then now I'm gonna do 255 times this. So I'm gonna copy this, make this my second one, and here's my G channel. This should be green. So now if I plot this, we should see a green channel. And it's not green because we have 255. This should be ones. And this should be zeros. Okay, so if I run this, we see green. And then I could repeat this. I'm gonna move my ones here, and then this will be zeros. And this now will be my red channel. Move this by accident, so ones, zero, zeros. And if I replicate this part and make this my third subplot, and this is my red image. So if I plot this, we should see all red show up. Okay, so that's how you could plot all the color channels. And then maybe you want to have black and white. So here you might have a black image. If it's a black image, then what you're gonna end up having is have all zeros instead. So if I do zeros here, and then maybe you have a white image, you have cv.merge. You're gonna have 255 times ones. Okay, so these will be all the highest pixel values. So if I do this twice, then if you want, you could put in a for loop, but for the sake of simplicity, I'm just gonna use it directly. So I have my black image, and then here I have my white image. So if I run this now, I should see my black and white images show up. Okay, so black and white. And notice that with matplotlib, what's nice is I could hover over it. Let me actually move it a little bit so you can see the values. So if you look at the bottom corner here, if you pay attention to this, you can see the pixel values. These are all white, which is 1. The black is 0. So here it actually converts the 255 from a high and low to 0 to 1. So the scaling factor is actually normalized to 0 and 1, as you can see. But if you're using OpenCV, it's normalized from 0 to 255. So you just gotta pay attention to that. But right now, yeah, like I said, it normalizes it for you, so that is taken care of. Okay, so sometimes when you're actually trying to plot the BGR channels of the image itself, you may actually end up seeing the grayscale values of the BGR channels. So what I mean by that is it depends on what you're trying to do, but sometimes you may want to see the actual colors. I'll show you how to do that in a later example, but this one here, I'll show you what happens when you actually try to look at the channels separately. So here I'm going to call this def BGR channel grayscale. So I'm actually not converting it to grayscale, but when you read it and try plotting it, it'll be grayscale, and I'll show you what that means. Let's call this BGR grayscale channel. So here what we have is we're going to go ahead and read our file. So we have root os.get cwd, and then I have my image path os.path.join, pass in root, and then I have my demo images, and then I call it cute pic1.jpg. And my image is going to cv.onRead, and then I'll pass in the path. And if I try splitting my channels to BGR, if I do cv.split here and pass in the image, what this does is it'll pass in the BGR channels separately, one by one. Okay, so that's what that function does. And each one will be a 2D array because it's one channel at a time. So I'm going to create some zero matrices and do np.zeros like. So this will make the same dimensions as my B matrix, and then maybe I'll also get some ones. Or for now, let's not worry about the ones. We'll just get the zeros. And perhaps you will want to plot it. So here we're just going to plot some of the channels. So here we have zeros. Actually, let's go ahead and plot the BGRs directly to see what they look like. So if I do plt.figure and then I do plt.subplot, I'm going to plot 3. So if I do plt.show, and if I show the different ones, if I plot B by itself, and I do plt.title, and then this is my B channel, plt.show. If I run this, you'll see what the B channel by itself looks like. So right now it's showing the values. Sometimes you may want to convert it. There's a cmap command that will make it into gray. Gray should be in quotes. So this will show the channel, the blue channel in grayscale essentially. And this should actually be in show. So if I run this, okay, we can see this is the blue channel in grayscale. So pretty much the black and whites will show you how much of the blue scale is showing. So if I repeat this 2 more times, and then here we have my other channel, maybe it's gonna be my green channel, and then my other one is gonna be my red channel. So if I run this, I would need to replace the plot numbers. Then that will show it in the 3 different subplots. So notice here, this is my BGR channels individually, but notice that is not red, green, or blue, right? So this is actually just showing when you actually plot the individual channels, it's not going to actually show the colors, because if you actually want to see only blue, only green, only red, you have to zero out the different channels, and that we will show in the next one. Okay, so now we'll see what the actual colors look like. We'll make a new function for that. And why not, let's call it something that makes sense. So we could say like BGR, channel, and then in color, okay? So we'll go ahead and call this function here. And inside, we're gonna do some same stuff here. So we're gonna read it, split it, but now we want to do some modification to the channels. So the modification that we'll do is we're actually gonna use our zeros. So zeros equals np dot zero like and pass in our B matrix. So this will give us some zero values. And if I recreate my blue image to be cv dot merge, and what we're gonna merge is our blue channel and then zero out the other channels. And then if I repeat this for the other channels, so we have B, G, R, but now it's gonna be in the different order. So B, G, R, and then this one will be zeros. This one will be zeros. So this will merge the different channels for my BGR and zero out the other channel. So if I go ahead and try plotting it, do plt.figure. So inside my plots, I'm gonna do plt.subplots and then 131 because I'll have 3 subplots, and then plt.show. Now I could show my blue image, and then repeat this part. So now this will be my second, and this will be my third. So I have my BGR and plt.show to show the plots. Now, if I run this, we should be able to see the different channels in color. Okay, so now that we zeroed out the different channels, we could see each individual channel in color. So maybe that's what you're expecting when we think of color channels. Okay, so if you found this video helpful, give a like and subscribe, and I'll see you in the next one. All right, so in this video, we're going to talk about grayscale images. Start off by talking about what are grayscale images, why do we need grayscale images, how do grayscale images work, and then jump into some coding examples on how to convert BGR image to grayscale, and then how to actually read an image as a grayscale directly. Okay, so what are grayscale images? So when you look at an image like this down here, it's in color, and then this one up here is in grayscale. So what a grayscale is essentially, here with color we have 3 channels, with a grayscale we have a single channel, and then all of these pictures are black and white pixels that can range from intensity between 0 and 255. Okay, now you might be wondering, why do we need grayscale images? So one of the main benefits is to reduce the amount of data, because when we have a single image, right, we have 3 channels, and then with a gray image we have only 1 channel. So 3 versus 1, obviously with a single channel you use a third of the amount of data. So a lot of times for certain pre-processing steps for image processing, it may be useful to just look at a combined channel instead of all 3. Okay, so how do grayscale images work? It's pretty simple. It comes down to an equation here. You take a scaled value of the red channel, a scaled value of the green channel, and then a scaled value of the blue channel. You sum it up, and then that will be your grayscale pixel. And depending on which convention you're coming from, these scaled values may be different, but these are the scaled values that you would use for OpenCV. Okay, so now let's jump right into our coding. Okay, so as usual, we'll import some of the stuff that we'll need. And inside our grayscale, what we're going to do is do our usual read, os.getCwd, and then my image path is going to be os.path.join, and then pass in roots, and I put my file in demo images, call it cubepic1.jpg. Okay, so I'm going to read in the file with cv.onRead and pass in the path of my image. So that will be my image, and then I'm going to have a gray one. And here I'm going to do cv.cvt color. What I'm going to do is convert it to grayscale. So pass in the image, and then there's going to be a code, so cv.color. So you can see all of these different options you have when you type out color. And if I do like BGR, you can see I could convert to these different types. Here working with the gray value. So the cv.color bgr to gray is going to actually give us some integer value that passes into the cvt color function that will then tell it that, okay, I want it to be a gray value, but this is just more of a human readable format. And then here, if I do cv.show, so now I'm using the cv show function, pass in my gray image, and then cv.wait key so that it will stay open. And if I run this, we should see a gray image of our kitty, okay? Okay, so moving on to our next example here, we want to actually read in the value directly as gray. So that will simplify a few lines of code for us. So I'm going to call this read as gray here, and I'll call it a function down here in my main. And what we want to do is all of this will pretty much stay the same. The main thing that we save is the single line of code. So instead of having to convert it, we could just pass in cv.read, and then you have this grayscale option. So now if I try running this, we will see that it'll just directly plot it as gray. So you save one line of code, but it's kind of up to preference depending on how you want to do it. If you already know you're gonna read it in as gray, then just do it that way to make your life a little bit simpler. Okay. So if you found this video helpful, give a like and subscribe, and I'll see you in the next one. All right, so in this video, we'll talk about the HSV color space in OpenCV using Python. So first, we'll start off by saying, what is HSV color space? Why do we need HSV color space? How does the HSV color space work? And then go into a cool example of HSV color segmentation of our cat. So what is HSV color space? So H stands for hue, we have S is saturation, and then V is value. So typically the hue is between 0 and 180. This is in OpenCV, but in practice, for other applications, you'll see it in 0 to 360, and that will show you the type of color. So here is the H value, and it goes inside a circle. That's why it's 360. I don't know why OpenCV uses 180. But with hue, pretty much is you're going around the circle to see which color you want. And with saturation, that is this here is the radius of this cone. So it will show you the concentration of the color. So as you move inwards, it gets lighter. And as you move outwards, the color is more concentrated. So you could kind of think of saturation as diluting your color with water. And then value is the up and down. So as you get lower, you can see it's a dark region, and then as you go up, it's a brighter region. So you could think of value as the intensity of your color. Okay. So why do we need HSV color space? So a common application is with segmentation using color. So by the end of this video, you'll see how we can actually do segmentation of this picture. And we're trying to get the fleshy part of the cat, which is kind of the pinkish color, which will give us the ears and kind of the nose area. And in general, HSV just gives you a more intuitive way of understanding and describing the colors as opposed to RGB, because with RGB, you kind of have three values for each number, and they don't really give you a good idea of what the numbers mean. Okay, so the HSV is a more natural way of doing that. So how does HSV color space work? Typically, you'll go with the three numbers and then you normalize it, divide by 255. And then you'll have what's called C max and C min, which is the max and min of these numbers. And then you find the difference between the C max and C min. Then you'll go through some steps to do the hue calculation. So depending on what you have, if C max and C min are equal, you set H to 0. If C max is equal to R, then you compute H with this formula. If it's equal to G, you compute it with this. And then if C max is equal to B, you compute it with this. Okay. So basically you have a piecewise function and then you compute it depending on what it is. And for saturation, if C max is 0, you set S to 0. And if C max does not equal 0, then you compute with this equation here. And then the value is just based off of your C max. And thanks for Geeks for Greeks for this algorithm. And now we will jump right into our coding example. Okay, so here we have a simple demo program. here I have HSV equals CV dot CVT color. And then this is the main command to convert it to the HSV color space. So BGR has 3 channels, HSV also have 3 channels, but the channels now are HSV. So we have color BGR to HSV here. So what we want to see is the values now. So if I put a debug here, and if I run my code, let's take a look. Let's see, debug Python file. So if I run this, we should see some values that we're dealing with. So if I look here, notice that HSV, right? The colors, the numbers I'm dealing with are these right here. So if I view value in data viewer, you'll see some of the values. And you can see here that this is also a 985 by 1170 by 3. It's going to be the same shape as our image. But the main thing is that the 3 channels, so the 3 layers or 3 dimensions of the matrix is going to be HSV instead. And you can see some of the values for this if you click into it. But right now, because I'm using the data viewer, is loading. And then usually a big file will take some time to load, but then after you get it, it should be pretty good. So I'm gonna look at the first axis and hit apply, and you can see these will be all the H values essentially. Okay, so that's what the HSV gives us. I'm gonna exit out of my debug, and now maybe I want to do some plotting. So with the HSV color segmentation, what you need is to do some upper and lower bound for our values. So we have np dot array, but let me first show you the actual value. So if I do plt dot figure, it's a lot easier to see it in the figure, so we will do that. So I'm going to plot the RGB value here to get an idea of some of the pixel values, and then plt dot show. So if I run this, so here the pixel values are 77, 56, and 53. So I could actually find out the corresponding HSV values. And from there I could figure out, what range I'm dealing with. So there's actually a pretty neat app that I use. So I use that app to figure out some of the colors. So let me show you that. Okay, so this app here lets you see the actual value. So if I drag this H, you can see which values I'm in. And then if I drag this, you can see the saturation. So for my example, if I'm looking at, you have some advanced controls here. So I could do 0 to 255, for example, radians percent, right? So you have different options. But here I think I'm going to go with degrees and then 0 to 255. Okay, so these will be my range of values. And then for my HSV, for the saturation, notice that I could choose these values here. My H, you could see, if I'm getting the years, then what I may want is uh, like around this area, 0 to 20. But remember, with OpenCV, I need to divide by 2, right? So I could choose somewhere around 20 here. And then with my saturation, you can see how bright you want it, right? So I don't want it too bright. I don't want it too saturated. So maybe I'm going to go with something like 120. This is my saturation. And then with the value that I'm using, it depends how dark I want it, right? So we know that the years are on the darker end of the spectrum. So we could choose somewhere around like 100. So this will be a good way to visualize what the range of pixel values we're trying to capture. Okay, so that's what we'll be using. So if I come back to here, that's we looked at a pixel, we kind of know what color that was, and then now we can actually try to have some upper and lower bound. So I'm gonna have lower bound equals np dot array, and these will correspond to the HSV values. Here I have a lower bound of 50 for Hough because, or HSV, I should say. So maybe I want to have like a range here. So V, if I go to 50, it's around here, right? If I get too low, this will be very dark. So I actually want to limit the value from 50 to 100 to get this region here, okay? This upper region. I don't want the very dark ones because I might end up getting a lot of the fur. So I'm gonna try to get the top region. So I'll do this for my lower bound. And then for my upper bound, what I want to do is have 0 to 10. We had 20 earlier. We divide by 2 because OpenCV is from up to 180 degrees. And then here I have 0 to 120 will be my upper bound. And then we create a mask equals CV dot in range and pass in the HSV channel. And then we have lower bound and then pass in upper bound. So this will take the ranges, my HSV matrix, and then give me a mask value. Okay, so once I have the mask, what I could do is I could use the masks to see the areas with the years. Okay, so if I do, I'm going to actually do cv.show for the mask, and then pass in mask, and then cv.weight key, pass in 0. And if I run this, we should see the mask pop up. First close the previous figure, and then now I run it. And you can see this is kind of the mask area. So I have 0 to 50, this should be 100. So notice if I didn't care about the V, it didn't turn out as good, right? But if I try running this again and close this, you can see I got the years pretty nicely. So you can play around with these values to see what features you want to extract, but with HSV, it gives you a really nice way to get different parts of the image with consideration of lighting and things like that, okay? So if you found this video helpful, give a like and subscribe, and I'll see you in the next one. All right, so in this video, we're going to talk about image resizing. Start off with what is image resizing, why do we need image resizing, how does image resizing work, and then jump into some coding examples. Okay, so what is image resizing? The basic idea is you make an image smaller or bigger. So here you can see a bigger one, and then here is a smaller one. And we'll get into details of how this actually happens. So you might be wondering why we need to do image scaling. Some of the main reasons is you want to reduce data. It's good for pre-processing. So if you have some certain steps, maybe you don't need quite all of the large resolution, you could reduce it. You can also improve the resolution if you're trying to zoom in and it's too blurry. So there's different applications. So how does it actually work? There's different methods to resizing, and these methods here are types of interpolation. So you have the nearest neighbor, which is essentially choosing the pixel value that is closest to. You have bilinear here, so you're pretty much interpolating between the 2 points using a linear interpolation. You have bicubic, which you might fit like a polynomial function. And there's also a lot of different types, but we'll see it in practice when we get into the code. Okay, so let's jump right into it. Okay, so as usual, we're going to import some of the modules that we need. Okay, I'm going to call my function image resize. And then if name equals main, and I'm going to call my image resize function. Okay, so I'm going to pass in my image root os.get cwd. And I'm going to have my image path equals os.path.join. And then I have my root. I have demo images cubepic1.jpg. And then I'm going to read it in. So image is cv.onRead. And I'm going to pass in my image path. And then I'm going to do some conversion using the cv.ctv color. And I'm going to convert it to RGB. So cv.color bgr to RGB. And then what I want to do is crop out part of the image. So I'm going to do image equals image, and I have some values that I figured out already. So 286 to 345, and then 322 to 389. And then the third column will be, the 3 dimensions will be the same. And I want to get the height and width equals image.shape. And this, I'll play with some scaling factors here. So I'm just zooming into part of the cat. Specifically, I'm going to get the eyes. And then the scaling, what I'm going to do is see how the scaling works. Okay. But here I'm going to do scale of 1/4. And then I'm going to try out different the interpolation methods. So I'm going to put it inside a list and call it interp methods. And you could see the different methods when you type cv.inter. So you have inter area, you have cv.interlinear, you have cv.inter nearest, and then there's a few more. You have a cubic, cv.inter cubic, and cv.inter the land sauce. Can't really say this, but it's the one that starts with the L. Okay, lank sauce. All right, so if I move on, I have gonna have some titles I'm gonna do. So interp title, and then I'm gonna have area, linear, nearest, cubic, in quotes, and then the last one that I can't pronounce. Okay, so those are 4 methods. I'm gonna have my plt.figure and plt.subplots. I have 2, 3, 1. So this is gonna be the original image. And then inside my for loop, I'm gonna show the different methods. So for I in range, and then do the length of my interp methods. And then I'm gonna do plt.subplot 2, 3, and then I plus 2. Then I'm going to do my resizing here. So this is a part that we can see the different results. So I can call this image resize, cv.resize, and I'll pass in my image. And then I need to cast my dimensions. So I'm using the width and times the scale. So that's how much I'm scaling it. And then the second dimension is going to be int of the height times scale, right? So that's the new size, and then we have our interpolation. It's going to be the interp method and pass in I. Okay, so now we could do plt dot show and then plot the new image, which is the resize. Add the title here so we know what we're looking at. And then lastly, we could do plt.show to see the result. Okay, so if I run this, we should be able to see all 4 methods. So this is a picture of the eye, and you can see the different resolution. So the original eye, the area, linear, nearest, cubic, and the last one. So this last one actually does a sync function interpolation, and it's supposed to give the best result. You can kind of see here the nearest is kind of loses this brightness spot here a little bit if you look at this area. So if I don't look as closely, you might be able to see a little bit better. So if I look at it from this view, you can see the different results. The area seems to kind of blur out this bright spot, whereas these 3 methods here seems to have the bright pixel here more obvious, okay? So that's zooming out. If I want to scale in, And if I run this, you can see that this is how it looks if it tries to make it clear. And you can see this one, the nearest and area seems to be more pixelized, whereas these three methods seem to be smoother. So depending on if you have like time constraints, you may choose one over the other. So it just really depends on what you're aiming for. But you can see for recreating a better resolution, these three actually works out pretty well. Okay. So if you found this video helpful, give a like and subscribe, and I'll see you in the next one. All right, in this video, we're going to talk about image histograms. Start off by saying what is image histograms, why do we need it, how does it work, and then go into three coding examples, one with a gray color, and then histogram of a region. Okay, so by the end of this video, we'll see how we can interpret an image like this of a cat into a graph like this on the right here. Okay, so what is image histogram? Image histogram shows the distribution of pixel intensities. So you can see we have pixel intensities on the x-axis and number of pixels on the y-axis. And here we have the three colors of the three different channels. So why do we need image histogram? There's a lot of applications. One is for thresholding, could be for equalization and enhancement of images. Could do different things like color analysis or even some color segmentation if the peaks are in very different places. So how does image histogram work? So the simple idea is you count the number of pixels for each pixel intensity. So here we have 0 all the way up to 255 as our max. And so for every pixels from 0, 1, 2, all the way up to 255, we count how many times this pixel value shows up, and then we just mark it. So here you could look at this graph and see the blue is the winner with the most counts around. If we draw down around 200 something for pixel intensity. Okay, so that's how the histogram works. So let's go right into the coding. Okay, so as usual, we're gonna import some of the things that we'll need. So we're gonna have our first function called gray histogram. So usually we want to just look at the gray sometimes because it's we're only dealing with one channel, so that saves us some time, and sometimes one channel is enough for us. So it's going to be case by case. But here we're going to go ahead and read in our file. So we have root equals os.getCwd, and then we have our image path, and that's going to be os.path.join, and we have our root, and our file is in the folder demo images, and then it's called cubepic1.jpg. Okay, so inside here we have our image equals cv.onRead, and then we're going to pass in image path, and we're going to read it in as a gray image, so onRead grayscale. Okay, so now if I go ahead and plot this plt.figure, and then plt.show, and we're using the matplotlib, so we have our cmap here equals gray. So this will plot our image in gray. Okay, so if I do a plt.show, we could see our cat image here. Okay, that's our cat image. And now if we want to do some histogram plotting, we could use the histogram function. We'll create a variable called hist and then set that equal to cv.calc_hist. And then what you want to do is pass in, it's weird, it has to be a list of your image because perhaps you may have more than one. And then you have your channel. So with only grayscale, we have one channel. The mask we won't use. And then 256. Later we'll talk about, I personally don't use the mask because there's an easier way to do it, which we'll show you later on at the end. Here we also have the range of values, which will be 0 to 56, and it's not including 256. That's why pixels is from 2 to 255, not including 256. That's why we have the number 256 here. Okay, so we're going to go ahead and do some plt.figure for a new figure, and then plt.plot to plot our histogram, and then we'll label our x-axis as bins, and then we will label our y-axis as number of pixels. Okay, so If I plot this, I should see my histogram plot in grayscale, and voila, we see that most of our values are around the 200, which corresponds to probably the bright background, and this white, the floor is white, this band is white. So we have a lot of high intensity values, which shows that there's a lot of close to white values in this image. Okay, so that's one interpretation of this. And maybe sometimes you would want to look at a color histogram instead. So I could do def color. I'm going to call this def color histogram. And then inside of here, we're going to do some reading as we did before. And then once we read the image, we want to, here is a different part. So we don't want this to be grayscale anymore. But what we want is to convert it to RGB. So we're going to do cv.cvt color and then pass in our image. And we have our cv.color, and it's going to be called color BGR to RGB. Okay, that will convert it to RGB. And then we have our plt.figure. We're going to go ahead and plot it, plt.show. And we have our RGB image. So plt.show will show the image. And if I run this, we should see our color kitty. But first, of course, I need to comment this out and then call our new function. And I need to close these figures. And then if I run it again, we should see our color image show up. So that's all working. So now what I want to do is get our histogram for our color channels. I'm going to define a color list called colors and then label this B, G, and then R. Okay, so I'm going to put some stuff in a for loop. So for I in range the length of colors. And you could do a Pythonic way if you want, but I'm going to do it this way. So cv.calc hist. So I'm going to calculate my histogram, and it's going to take the same inputs as we did up here. So I'm not going to rewrite it. The only difference here now is instead of image, we call this image RGB. Okay, so now we're going to plot it. So plt.plot, and we have our his, colors, and then I. Afterwards, we're going to do our label. Our labels will be the same. So I'm just going to copy this. I need to create a new figure right here. So plt.figure. And this should actually be pixel intensity. That would make a little bit more sense instead of bins. Okay, so I actually want this index here to be I so that it'll correspond to the different channels. Okay, so I'm going to update that and then run it again. But I need to first close this. So if I run it, now we see our 3 channels. Okay, so that's what we're expecting. So what this tells us is that this image here could actually be represented by this on the right. And we can see that the red values have a lower peak, the blue values have the higher peak. And not just that, you can see that the red is lower in pixel intensities for the peak, and the blue is higher in pixel intensities. So that tells us a little bit about the distributions. And we also see here, if we zoom in, there's some local peaks. So that may tell us some information too, if we were to look into that. So next up is we're going to do some segmentation of a region. So region might be helpful if we want to zoom in to somewhere and then see what's going on. So here, if I look at my image again, let's say if we wanted to zoom into a special region, so maybe here in the 600 to 800s, we want to see a distribution of this little logo here. So what we want to do is, let's go ahead and replicate this. So we're going to call this histogram region. I'm going to comment this out and then call our new function histogram region. So the main difference now is that all we got to do is, instead of using a mask, what I prefer is just to truncate our image into a new section. So Here we're just gonna go ahead and get part of the image. So I define 675 to 825, and then 600 to 800. Okay, so if I go ahead and run this, we'll see what this is doing. We're getting a region of this, and you can see the peaks are a little bit shifted, a little bit higher. Okay, so this might be some useful of information, and you could choose these values wherever you want based on where you want to zoom into your image and see what's happening locally. Okay, so if you found this video helpful, give a like and subscribe, and I'll see you in the next one. All right, in this video, we're going to talk about 2D convolution, talk about what it is, why we need it, how does it work, and jump straight into a coding example. So by the end of this video, we will understand what this image here means on the right, and how we could convert this image here to this image here on this side, okay? So what is 2D convolution? So the idea is we have a sliding kernel matrix. So kernel is just some matrix that we have, and we do a element-wise multiplication on the input image. So we're going to slide this matrix and do element-wise multiplication, and we'll get into more details of what that means. So why do we need 2D convolution? So one of the main applications is for smoothing or blurring images. This is an example here where we're blurring the image. It might be good for feature extraction, image enhancement, edge detection. Whenever there's a kernel and you want to slide the kernel across the image to produce a new image, we will need 2D convolution. So how does 2D convolution work? So we showed this picture earlier. The way this works is we have a kernel. In this case, we have a kernel that is all ones and divided by 9, or the 3 by 3 times 3, which is it counts how many number of ones is in here, and that will essentially give us our mean. So this is actually a mean filtering or average filtering. So what this does is it will add up all these numbers. So these are all the numbers inside this box here, and then divided by 9, which will give us 46. So just imagine if I were to have this box and slide it over, one by one, right? If I repeat this one by one and keep sliding it and keep getting a new number and just do this all across and all the way down, and eventually I will get this new generated image here based on me sliding this kernel across the original image kernel, okay? So if there's going to be 3 channels and you do it for all 3 channels, if it's just one channel, then it's just one 2D matrix. Okay, so let's jump right into a coding example to see how this works. Okay, so as usual, we're going to go ahead and import some of the modules that we need. Okay, so we're going to call our function here convolution 2D, and then we're going to have our usual main function if name equals main. And inside of here, we're going to call our convolution 2D function. So inside our convolution 2D function, what you want to do is read in our image. So root.os.getCWD and get our image path, os.path.join, and then pass in root. And our image is in demo images, and it's called tessa.jpg. And then inside of here, we're gonna go ahead and read our image. So cv.read and pass in our image path. Okay, so now we're ready to convert it to RGB. We're gonna do RGB equals cv.cvt color, and then pass in image and cv.color. It's gonna be BGR to RGB. Okay, so now we have our color image. We're gonna choose some size for our kernel. So here we're gonna make our own kernel, but usually in OpenCV, a lot of times there's gonna be functions that can create the kernel for you. Okay, so here we're gonna go ahead and make our own median or average filter kernel. So it's gonna be all ones. So the size is gonna be n by n, and then it's gonna pass in the data type of float 32. And we want to divide it by the number of elements in there, so it's going to be n times n to get the average. So our filtered image, we're going to call img filter. It's going to be cv, we're going to use the filter 2D function, so this will call the convolution, or it actually is doing the convolution for us. So image RGB, and then you can see the inputs here. If I hover over it, this should be capitalized. 2D. So now if I start typing, you should see you can see the source and the depth. So the depth you could set to -1 since we don't care about that right now. So image RGB, you're gonna put -1. And then we have a kernel size, which is, or I mean our kernel that we're using, which that we define. So we'll just pass in our kernel. So this will do our filtering for us manually by us creating our own kernel. And then here we're gonna go ahead and start plotting our images. So we have plt.subplot. So we have a 1 to 1, and then plt.show, and we have our image RGB, right? So we could take a look at our original image first. So if I run this, we can see our original image. Okay, so this is our original image, and then now if we want to apply our filter, or we just applied it, but now let's plot it. So subplot, we have 1, 2, 2, plt dot show, and we're gonna pass in our image filter, right? So if I go ahead and run this, we should see our filtered image using this kernel of ones. So you can see the image has now become a lot blurrier, right? So that's the idea of convolution is we just this one simple line of function will do convolution, and then we will get our resultant blurred image. So if you found this video helpful, give a like and subscribe, and I'll see you in the next one. All right, in this video, we're going to talk about average filtering in OpenCV using Python. So we'll start off by saying what it is, why we need it, how does it work, and jump straight into a coding example. So by the end of this video, we will see how we could transform this image here to this blurry image here on the right. So what is average filtering? Average filtering is doing 2D convolution to get the average value of the neighbors, okay? So why do we need to do average filtering? It's good for smoothing and noise reduction. So you can see here that even though we may not want to smooth out this nice looking picture, here we're just doing it for the sake of showing how you could smooth it out. So how does average filtering work? We will do convolution using this kernel here. So this kernel is 3 by 3, but you could actually choose this to be any size. So in general, it could be n by n, where n could be any value. Okay, as long as the kernel is not bigger than the image, up to some constraints. But usually, it's going to be a lot smaller than the image. Okay, so let's jump straight into a coding example. Okay, so as usual, we're going to go ahead and import our modules that we need. So we're going to go ahead and call our function average filtering, and then our if name equals main, and we're going to call our average filtering here. Okay, so inside our average filtering, let's go ahead and read in our image. Okay, so we have here, once we read our image, let's go ahead and create a window name, and we're just going to call this average filter. So we need a named window, pass in our window name, and we have create track bar here. We're going to make a track bar, and the track bar name is going to be called n for the kernel size, our window name, and then our initial value and the max value, we're just going to cap it at 100. And we need a callback function here. So we'll have a callback, pass an input, and then pass because we are doing nothing right now. So that's our callback function. And then once we have our image here, right? And then we created our track bar. The image I have is a little big, so I'm gonna size it down. So image.shape here, and then I'm gonna have a scale factor of 1/4, and my new width is gonna be a scaled version of that, and likewise my height is gonna be a scaled version of that as well. So this is our new height and width, and then now I could create my new image. Yeah, I'm gonna do cv dot resize here, and I'll pass in my image and my new width and height. Okay, so this is my new smaller image. So inside here, what we want to do is check out our track bar to see how changing the kernel size is going to have a different influence. So cv.wait key, and if we press Q, it's going to quit. Okay, so so our breaking condition. And then let's go ahead and read in our trackbar value. So cv.get trackbar position, the name of our trackbar, and our window name. And then we're gonna go ahead and filter our image using, there's actually a cv.blur for the average filter. And you need to pass in the image and the size of your kernel. So here we're using a square kernel, so it's the same size for the X and Y. So now I'm going to do cv.show, pass in my image name, and then pass in my filtered image. And then when everything is closed out, we want to destroy all windows. So if I go ahead and run this, we should see some image with a track bar. So right now it's set as 1. So you can see if it's 2, 3, you can see it's slowly getting more and more blurry, right? So as this kernel size is increasing, we're averaging more and more pixels. That's why it gets more and more blurry, okay? So you could go ahead and play around with the trackbar and see how much blurriness you have. So you can see a problem with this blurring is that a lot of the edges are lost because everything is just blurred together, right? So later on, we'll talk about some filtering techniques that could actually blur and still preserve these edges, which was pretty interesting. And you'll see that in a later video, okay? So if you found this video helpful, give a like and subscribe, and I'll see you in the next one. Alright, in this video, we're going to talk about median filtering in OpenCV using Python. So we'll start off by saying what it is, why do we need it, how does it work, and jump straight into a coding example. So by the end of this video, we will see how we could transform this image here with a bunch of noise to this image here that is pretty much noise-free. So what is median filtering? It's a method that finds the median value within a given region. Okay, so we'll see how that works later on. So why do we need median filtering? It's good to remove noise and for some cases to preserve edges. And how does it work? The way it works is you have a kernel here. So here we have a 3x3 kernel, and we will look within the kernel and then choose the median value. So if we list out each number here, right, we have each number listed out, and the middle number is our median, and that will show us our value that we're keeping. Okay, so the reason why it works so well with noise, especially the salt and pepper noise, which will generate noise of either 0 to 55, is because it's going to be in the extreme values, right? It's always going to be outside of the median, so it will always get filtered out. So that's why in this case, there was a noise of 255 here. That will go away. So let's jump straight into a coding example to see how this works. So we're going to call our function median filtering. So here we're going to read in our image, and now we convert it to RGB equals cv.cvt color. And then pass in our image cv.color bgr to RGB. Okay. So here we're gonna generate a noisy image. First off, we're gonna make a copy of our original image. So image RGB.copy. And then what we're gonna do is create some noise probability. You could probably tune around these numbers to see what works for you, but here I'm gonna use 0.05. And then create some noise using mp.random.rand and pass in the shape of our noisy image. So that is the same shape. This should be noisy image dot shape here. So noisy image dot shape, and then pass in 0 and 1 for the width and height. And then here we have noisy image, and we'll say if the noise is less than the noise probability divided by 2, we're going to set it equal to 0. And then similarly, we're going to do noisy image. Here we're going to say if the noise is greater than 1 minus noise probability divided by 2, that will equal to 255. Okay, so this is just some simple method to add in some noise, and we could go ahead and see how that looks like. So plt.figure, plt.subplot, 1 to 1, and then plt.show, pass in our noisy image, and then plt.show. So here we will take a look at our noisy image that we have generated. Okay, so it's a salt and pepper that we have. If you zoom in, you can see that it looks like a very dirty car. So let's go ahead and remove that dirty car. We want to make our car nice and clean. So we will apply our median blurring filter. So image filter equals CV dot median blur, and then pass in our noisy image. And then here is our kernel size. We'll use a kernel size of 5. So we'll go ahead and plot our image. So plt dot subplot. It'll be our second subplot, and then plt dot show, and we'll pass in our image filter. Okay, so now we should see a nice and clean filtered image. So now you can see our car is nice and clean. So it's all good. So that's how the median filter works. So if you found this video helpful, give a like and subscribe, and I'll see you in the next one. Alright, in this video, we're going to talk about Gaussian filtering and OpenCV using Python. So we'll start off by saying what it is, why do we need it, how does it work, and jump straight into a coding example. So by the end of this video, we'll see how we could use this kernel here to convert this clear image to this blurry image. So what is Gaussian filtering? It's a filtering method that uses a Gaussian kernel for convolution. So this thing right here is called a Gaussian kernel. So why do we need Gaussian filtering? It's good for smoothing noise or just noise reduction, and also for general pre-processing techniques. So how does the Gaussian filtering work? So Gaussian filtering, the way it works is this is the equation for a Gaussian. So this is for 1D, this is for 2D. And the way it works is it generates this kernel here. So this is a 3D plot. And you can see that it follows like a Gaussian distribution curve. So what this means is that, in the center of the kernel is going to take the most weight, and then as it goes outside, it'll take less and less weight. So there's this sigma term here, and this controls how skinny or fat it is. The fatter the sigma is, or the bigger the sigma is, the fatter the kernel, and the smaller it is, the skinnier. So, you can have ranges of like fat to skinny kernels here. And then this image here on the bottom is a 2D view. So you could think of this as like a top view of this 3D image. And this is what we will be convolving as our kernel, okay? So let's jump straight into a coding example. We're going to go ahead and make our function called Gaussian filtering. Here we have our Gaussian filtering. So we want to go ahead and read in our image. So root equals os.get cwd. So that's our root path. And we want to have our image path is going to be os.path.join, pass in root. And then we have demo images. And we have tessa.jpg. Okay, so we have our image path, and image equals cv.read. And we'll pass in our image path here. So now we want to start filtering. We want to let's take a look at how these kernels actually work. So let's have a kernel size of 51 for now. We'll create a figure, plt.figure. And then here we're going to do plt.subplot. We want to plot the two Gaussian kernels side by side, so we can see the comparison between the 1D, the 2D, and 3D. So kernel equals the Gaussian. There's going to be a function called Gaussian kernel. So we're going to go ahead and make the Gaussian kernel function. So we're going to call this Gaussian kernel, and this will take in the size and sigma value. Okay, so here we're going to set kernel equals to cv.get Gaussian kernel. So the get Gaussian kernel function actually just passes the filter coefficients for 1D. So we need to do some magic to make the kernel happen. So we'll pass in kernel again and do np outer, and then we'll do kernel and kernel. So this will give us our 2D kernel. So we'll return kernel. Okay, so that is okay. So we have our Gaussian kernel function here returning our kernel. So now we can call our Gaussian kernel function. So we have our Gaussian kernel function, and we're gonna go ahead and pass in our kernel. So we have our size n here, and then we'll check out a sigma of 8. So now we have our kernel, and then we could do plt dot show and then pass in the kernel. So if we do a plt dot show, we should be able to see our 2D version of our Gaussian plot here. Okay, so that's our Gaussian kernel. And then if we want to see a 3D version, let's go ahead and add a 3D version in here. We'll have a AX for our plot. We'll have a fig equals add subplot. We'll do a 1, 2, 2, and then we want to do a projection equals 3D. Okay, so now we could do x equals np dot arrange and go from 0 to n, and the step is 1. And likewise, we'll do it for the y. Okay, and then now we could do a mesh grid. So we have x, y equals np dot mesh grid, and then pass in x, y. And now we could find z equals kernel dot flatten, and we do ax dot plot surface and pass in x, y, our kernel. Actually, we're not going to be using the z value here. So we have xy kernel, and then our CMap is going to be called Viridis. And if we go ahead and run this, we should see our mesh grid plot. Okay, so this is how our kernel looks like. And let's just kind of tweak the sigma value. If we made this sigma a 2 and run this, we should see the kernel got a lot skinnier, right? So we could play around with this sigma value, and that essentially tells us how we're doing the filtering. So depends how much smooth transition you want or how much weight you want in different parts of the image. So you could play around with that value. So let's take a look at 4, somewhere in between. So yeah, you could play around with that is. And sometimes there's it'll automatically calculate that for you. You could, if you don't specify it, you could calculate it for you. Okay, so let's go ahead and make a function to do our filtering. So here we will have a window name because we're gonna play around with a trackbar. We'll call this Gauss filter. And then we have a named window we'll call win name. And then inside we're gonna create a cv dot create trackbar, and we'll pass in the trackbar is gonna be controlling the sigma, so we can see how the sigma value is affecting it. And we'll start it off at 1 and change it to 2, or go up to 20. I mean, and then we're gonna pass in a callback function. So our callback here, we're gonna just do nothing for now. So we're gonna have a def callback and then pass in input. And we're just gonna say pass because we're not doing anything for now. And our image is a little big, so I want to resize it. So we have our height width is gonna equal to our image dot shape here, and we're gonna scale it by 1/4, and then we'll have our new width equals int width times scale, and we'll do the same thing for the height. So we have height here, and then we have our new image. It's going to be cv dot resize, and we're going to pass in our image and then our width and height. Okay, so that's going to resize it for us, and then now we'll go ahead and put it inside our loop here so we can see it change. So we'll say while true, have an infinite loop, and then set up our breaking condition. So cv waits key, and if we hit the key q, we'll do ord q, and then it's gonna break if we hit the q key. Okay, so now we could extract our sigma value as we slide the trackbar using the get trackbar position, tell it the name of our trackbar, and then pass in the window name. And now we could filter our image here using the cv dot Gaussian blur, and we could pass in our image and then the kernel size and our sigma value. Okay, so that's our filter image, and then we could do cv dot show and then pass in the window name. and then the image filter. Okay, so now we could go ahead and just have our destroy all windows after we quit. So we should have a little app here that can help us see our, I'm going to close this, so we can see our sigma value as we drag it. So you can see this was sigma, um, sigma 1, 2, and if I slowly drag, it gets more and more blurry. Okay, so this might be a good way to tune your sigma values to see how much blurry you want, how much blurriness you want in your image. So if you found this video helpful, give a like and subscribe, and I'll see you in the next one. All right, in this video, we're going to talk about image thresholding in OpenCV using Python. So we'll start off by saying what it is, why do we need it, how does it work, and jump straight into a coding example. So by the end of this video, we'll be able to see how we could go from this image here on the left to this image here on the right. Okay, so what is image thresholding? So image thresholding is an image processing technique, and it converts parts or all of the image into binary. Okay, so here you can see on the right, binary pretty much means black and white. So in our case, it's going to be 0 or 255. So either of those two values. So why do we need image thresholding? So the reason why we may need it is for certain things like image segmentation, feature extraction, or object detection, and it's pretty useful for a lot of pre-processing steps. So how does image thresholding work? Well, there's a couple of types presented in OpenCV. So one of the main ones here is called thresh binary. So what this one does is based on your value. So this is your output image after being thresholded. That's what the DST here means. And then your input is the source. So if your input pixel is greater than whatever threshold you set, then the value will be your max value. So in this case, our max value is 255. Otherwise, it's going to be 0. So for the inversion one, it's just going to be the opposite. So these two values are pretty much swapped from this one. And then you have a thresh trunchold or truncate. What this one is, so if the source is greater than the threshold, then it'll be the threshold value. Otherwise, it's going to be the original pixel value. So main difference here is that instead of max value, you actually just set it to your threshold. And then instead of 0, you're actually setting it to your actual original pixel value. And then you have thresh to 0 here. So what this says is if your image pixel is greater than your threshold, then just set it to your original image pixel. Otherwise, you let it be 0. And then this one here is just the inverse of this. So these two lines here are switched. And here on the right, this is just a visual representation of what we just described here. So whichever way makes more sense to you, you could go with that. Me personally, looking at the left here is enough for me, but you could take a look at this if you want a more visual understanding. So to kind of correlate it, you can see this one right here is your original signal. And then here you can see that you're either gonna be the max value or gonna be 0 based on your threshold. Okay, and you could kind of follow the same thought process through the other ones. Okay, so how does it work? A little bit more detail. Typically, you need to choose a threshold value. So just depending on how you want to choose the threshold values, there's a lot of different ways. But some of the more useful ones is you could plot a histogram like we have here, and then based on the histogram, you could decide, maybe how you want certain groups of pixels or peaks to be split in half. So we'll kind of see more in detail how that influences the results. So a potential value here is where the peak split, and obviously where the peak split could be defined differently, but in the example that we'll be talking about today, we'll kind of choose somewhere right where it dips so that, the two peaks are kind of exactly separated somewhere in the middle. And we'll see how the results for that turn out. Okay, so let's jump straight into the coding. Okay, so as usual, let's go ahead and import some of the main things we need. And inside our threshold function, let's go ahead and do some of our image reading. So we're going to read our image. And then next up is we're going to convert it to grayscale because a lot of times thresholding is done in grayscale. So here we have cv CVT color. We could have also read it as gray, but I'm just gonna do it this way for now. So CV dot color and then BGR to gray. Okay, so now we have our grayscale image. So let's go ahead and take a look at our histogram. So we have hist equals CV dot calc hist, and then we're gonna pass in our gray image here. So after we pass in our gray image, let's go ahead and pass in 0, none, and then 256. And we'll go between 0 and 256. Okay, so I have a histogram video if you want to check it out for more details of this. But here I won't go too much into detail because I covered it already. So let's go ahead and plot our figure. So we have plt.figure and then plt.plots and then hist. And then plt dot, let's go ahead and label our axes. So we have our X label and our Y label. So our Y is going to be number of pixels. And let's go ahead and show, let's go ahead and show our plot. So if I run this, we should see the histogram plot like we saw earlier. Okay, there we go. That's our histogram plot. So again, we're going to choose a value somewhere here so that I kind of want to have these two peaks split in between since those two seem to be the major peaks. So let's go ahead and see how the different thresholding type behaviors will change our results. So let's go ahead and create a list called thresh opt, like thresh options. So to see the possible options, you type cv dot and then thresh, you can see the different options show up. So you have cv.thresh binary, you have cv.thresh. The other one I'm going to do is binary inverted. We have cv.thresh. The other one is 2.0. And then we have cv.thresh. You have 2.0 inverted. And then lastly, we have cv.thresh truncated. Okay, so those are our options. And let's go ahead and create a list for the names. So I'm going to call this thresh names, just so when we plot it, we're going to know what we're plotting. So we have binary, binary, inverted. We have a 2.0, and then we have a 2.0 inverted, and then we have a truncated. Okay, so those are our different options. And then let's go ahead and put this in a for loop to plot everything. So let's make a new figure and then plt.subplot for the first one. We're gonna make 2 rows, 3 columns, and then for the first image will be our grayscale. So plt.show. And then we have our grayscale image, and then CMap is gonna be gray. Okay, so let's go ahead and just do a quick show to see our pretty image. So if I run this, our histogram pops up here, right? And then we have our image that we're working with. Okay, so let's go ahead and start thresholding. So we're gonna put everything in a for loop. So for I in range, and then we have the length of our threshold options here. So because we have our subplot, the first one is taken, and we want to plot after the first one, we're gonna do 2, 3, and then it's gonna be I plus 2 because it's indexed from 1, so we need to increment 2 to start with the second subplot. And then from here we have PLT, or we're gonna use a threshold function. So this is the main function in this video here that's new. So we have our CV dot threshold, and then we pass in our gray image here, and this is a threshold value. So we're going to choose somewhere around 70, which is where the dip was that we said, and then our max value we're going to be 255 because that's the range we're dealing with. And then our thresh option is the options that we created in our list, so that way you can see all the different options. So if I go ahead and do plt.show, it's going to be my image threshold. So notice here that the threshold is going to return the return value and the final image. I don't care about the return value right now because we're going to assume that everything is working. So that's why I have this little line here that I'm just essentially ignoring the return value. So I'm going to pass in my image threshold to my show, and then go ahead and make sure it's gray for the CMap. and just add in our title here. So call this thresh names, pass in I, and that should be all. So if I go ahead and run this, we should see our different threshold types, and we could take a better look at what's going on. So that's our histogram plot that we don't need right now, so close it out. And we could see here, this is our original image, our binary. So you can see it did a pretty good job getting most of the background away. And you can see the car is in blue. So we kind of separated the foreground and background. And you can see here the binary inverted is just these two images inverted as expected. And then to 0, you can see that's we kind of focusing in on the car to be the dark, whereas to 0 inverted, we're focusing on the background being dark. And you can see this has like kind of cool metallic look. And then you can see the truncated, it gets kind of more of the background washed out. And then you can see the car is kind of the main focus. Okay, so depending on different applications, you may want to play around with different thresholding options and thresholding values and see what works best for you. Okay, so if you found this video helpful, give a like and subscribe, and I'll see you in the next one. Alright, in this video, we're going to talk about image gradient in OpenCV using Python. So we'll start off by saying what it is, why do we need it, how does it work, and jump right into a coding example. So by the end of this video, we'll see how we could get these two images here and the difference between the two. Okay, so what is image gradient? The idea is to find the first or second derivative of an image, and we'll see how that works. Okay, so why do we need it? It's good for things like edge detection, for feature extraction, and also image enhancement. So maybe sometimes you have an image and there's parts of the image you want to identify. This is good for those applications. So how does it work exactly? You have a filter that you convolve with, and what you convolve with is called a kernel. There's typically 3 different types. These are the more popular ones. So you have the Sobel X, Sobel Y. These two here are first order derivative kernels. And notice the structure here is -1, -2, -1, zeros in the middle, and then 1, 2, 1. And for the Sobel Y, it's going to be transposed, so it's going to be rows instead of columns. And for the Laplacian, this one is going to be a second order derivative. You see a -4 in the middle, and then ones in the 4 locations here. Okay, so you'll just have an image, and then you convolve it with this filter. And this is for 3x3s, but typically you could expand this to different sizes. And we'll see how in some of the coding examples how we could expand that to different cases. Okay, so let's jump right into a coding example. Okay, so as usual, let's go ahead and import some of the modules that we'll need. Inside our function, let's go ahead and read our image. And let's go ahead and take a look at our picture. So plt.figure, that's our image. And lastly, we'll just do a plt.show to show our image here. So that is our picture. And we can also do a CMap here if we wanted to see it all in grace instead of color. So if I run this again, we should see it all in grayscale. Okay, so now let's go ahead and let's first take a look at the Laplacian. So we're going to call this Laplacian, and CV, the function is also called Laplacian, and takes the input as the image and then the d depth. This here, we're going to pass in the type here, which we're going to be 64. And this is for high resolution. And then case size, we're going to pass in 21. We're going to use a pretty big kernel because our image is pretty high resolution. So plt.subplot here, and then 222 is going to be our second image. And plt.show will plot our Laplacian and then CMap of gray. Okay, so if I run this, we should see our image here. So notice it looks like nothing at first, but if we zoom in to the Tesla logo, for instance, we could see the edges of the Tesla logo has been identified. So that's for Laplacian, is usually unidirectional, and when we look at the other filters, you'll see more of the difference why we call this unidirectional. but essentially it's sensitive to both the X and Y direction. Okay, so let's take a look at the other filters. Well, there's actually ways to generate the kernel if you're interested in the kernel. So we'll take a look at that. So let's say we have kx, ky. The function is going to be called cv.get deriv kernels. And then here we pass in the derivative in the x direction, which will be the first order, and then 0 in the y. And let's say we're passing in the 3, and we'll see how it looks like. So if we do print, and then ky matrix multiply kx dot transpose, and if I run this, we should see our kernel here. Let's go ahead and close this image for now, but if I drag this over, you can see this is our kernel. So this matched what we saw in the beginning, okay? So let's go ahead and use this filter, but with the Sobel function itself, since it's built in. So you could do cv.sobel here. So here it'll take in the image, and then again, the second argument is going to be the cv.64. So this will guarantee a high resolution. So the issue is if you have two edges, sometimes you use a lower resolution for the data type, then you may miss an edge. Okay. So that's why we're going with the highest resolution. So here we do a case size equals 21. And if I do plt.subplot and 223 and plt.show, and we'll pass in my Sobel X and CMap of gray. Okay, so if I go ahead and run this, we should see our Sobel X. So if you notice, you can kind of see the lines, edges in the X direction or the vertical. And if I zoom into the logo, we can see that this logo here has captured a lot of the edges on the right and left side, but top and bottom, not so much. Okay, so if we go ahead and do the same exercise for the Y, just going to do a little tweak here, make this 0, make this 1. This will stay the same, and then Sobel here, this will be a 0 and then a 1, so we're just switching the X and Y, and then go ahead and modify this. And then this one here, we could modify to be a Y. Okay, so now we should see our Sobel Y. So if I run this, we'll take a look how that looks like. So first off, you can see our kernel here. It has been transposed as we expected. And then in here, if we look at the actual image, you can notice here some of the horizontal lines or in the Y direction has become more prominent. And if we zoom into the logo, we can start comparing the difference. Okay, so notice that for the Laplacian on the top right, the edges in both x, y is all pretty clear. Whereas here in the Sobel Y, the horizontal is more clear and the vertical ones are kind of faded, right? But with the Sobel X, you can see the vertical or in the X direction, it's a lot more prominent. Okay, so that's the main difference with the different kernels. So if you found this video helpful, give a like and subscribe, and I'll see you in the next one. Alright, in this video, we're going to talk about Canny edge detection in OpenCV using Python. So we'll start off by saying what it is, why do we need it, how does it work, and jump straight into a coding example. So at the end of this video, we'll see how we get this image here on the left to this image here on the right. And we'll actually be making a little trackbar application, which will have some fun with the threshold values. Okay, so what is Canny edge detection? It's an algorithm that's typically more robust than standard gradient methods. So a lot of times when we just do normal gradients, the result might not be so good. So in those cases, you may have to rely on the Canny edge detection. Okay, so why do we need it? Like we said, it's going to be more robust or more reliable, but in general applications, you might use it for things like object detection, image segmentation, or feature extraction. Okay, so how does it work? The way it works is typically there's going to be a smoothing application with Gaussian filter, and then the gradient of the image is going to be applied using a Sobel, which we talk about in image gradients, and then we're going to be applying a non-maximum non-maximum suppression technique to find the local maximum. So what this does is if you have like a thick edge, it'll transform it into a thin edge. And the idea is, if there's if you have like a lot of peaks, there's going to be like one peak that's the maximum, and then you just ignore the other peaks. So that's the idea with this, because you could have a bunch of peaks here, and maybe only one of them corresponds to the peak. So that is what non-maximum suppression is. And then you have double thresholding to keep the edges that go above the max threshold, even if connected edge dips into region between the max and min threshold. So we have a couple of cases that we can look at here. So we have two thresholds, typically a high and a low. So if you have an edge and it's all above the high threshold, then we keep it. Okay, but here we have a B and C. So if you have part of an edge that's above, but it's connected to another edge that is between high and low, we still keep it. But if you just have an edge like E, which is just between high and low, and it's not passing the high threshold, then we would discard E. Okay, and then if you have something that's below the low threshold, we also discard it. Okay, so the only ones we're keeping would be these two cases. Okay, so this we keep, keep, keep. Okay, so that's the idea of the canny edge detection. Okay, so let's jump right into a coding example. Okay, so as usual, let's go ahead and read in some of our modules that we'll need. And we're going to call our function here canny edge. Inside our canny edge, let's go ahead and read in our image. Then we want to convert BGR to RGB. Okay, so now we have our color image. Let's go ahead and rescale our image because it's a little big. So we have height, width, and then the third argument, which we don't care about, image.shape. And then what we want to do is have a scale factor. We're going to get 1/5 of the image. And we're just scaling it because if it's too big, it'll take up, it'll go out of the screen. So that's the main reason. So we're going to call this height scale, and then we'll cast it with an int. And we have height times our scale. Then we'll repeat the same thing for the width here. Okay, so we have our height and width scaled. And then our new image, we're just going to use a cv.resize function. And we'll pass in our image and a tuple, which will be our width scale and then our height scale. And then our interpolation method, we'll just go with cv dot inter, go with the linear is fine for this. Okay, so we have successfully resized it. And we'll do some fun with a track bar. So we have a window name, which we will name Canny. And then here we're going to do cv.named window and then pass in our window name. And we'll create our two track bars. So cv.create track bar, and then we have the name of our track bar, which will be min threshold. And we'll pass in our window name, and then our value 0, and then 255. And we'll need a callback. So right now our callback, we're actually not going to do anything. So we'll have a placeholder, and we'll just call pass. Okay, so this will be our placeholder function. So we'll repeat the same thing for our max threshold here. So that will be pretty much the same. And then we'll put it inside a loop. So while true, can't type right now. So while true, what we want to do is have an escape. So if cv.wait key, and if that equals the q key, so q for quit, we're going to break out of this. Otherwise, we will extract our min threshold value using cv.get track bar position, and the name is going to be min thresh. And we'll pass in our window name. Then we'll repeat the same thing for our max. So here, we're going to just change this to max. So we have our two track bars we're getting positions of, and then we'll update our cv.show here with our canny function. So we have our window name, and we could go ahead and call our canny function here. We're going to just call this canny edge equals cv.canny. So what takes it in is the image, and then our min threshold, and then our max threshold. Okay. So here, lastly, we'll pass in our canny image. And then all we gotta do now is just have close with destroy all windows here. That way, when we're done, it'll close out. So if I go ahead and run this program, we should see our results. So notice here we have our min threshold and our max threshold. So if I slowly increase the max threshold, you can see more of the good edges show up and some of the nonsense edges start disappearing. So if I drag it all the way to the end, you can see that's how it looks like. Now if I start playing with the min threshold, notice what happens. Some of the edges gets better and we could see a lot more of the car. Okay, but notice when the car structure starts getting clear, I'll lose some of the details of the seats, right? So that's kind of the drawback. And you just kind of have to find a balance between what you want. So here you can see a lot of the car seat detail, but here it's better. Okay, so for me, I kind of like somewhere in between here. Maybe this is a little bit lower. So something like this might be pretty good. And then maybe you could apply like a secondary filter to have the results look better. Okay, so if you found this video helpful, give a like and subscribe, and I'll see you in the next one. Alright, in this video, we're going to talk about the hue line transform in OpenCV using Python. So we'll start off by saying what it is, why do we need it, how does it work, and jump straight into a coding example. So by the end of this video, we'll see how we could get this line here identified in this picture on the right. So what is hue line transform? It's the idea to extract lines from an image through a series of different steps, as we'll see later on. But you can see one of the main distinct lines you can see in this image is this line here on the road. And you can imagine if it's for like autonomous driving, that could be an application for lane detection. So why do we need hue line transform? It's good to extract lines. It's also good for noisy or segmented lines. So maybe there's like missing information here that we're extrapolating. So here you can see it's extrapolating the rest of the line even though it can't see it. So how does a hue line transform work? The idea is you have to first parameterize a line based off of two parameters. So here we could define a line by an angle. So you have an angle, and then you also have a distance that we will call d here. So angle is theta, and then we have our distance d. And the idea is as long as you could parameterize the line in such a way, you could describe the line based on all the variations of these angles for each distance. So the first step of the process is to find the edge of the image using Canny edge detection. And then for each pixel in the edge of an image, so imagine if you run Canny edge, you're going to have all the potential candidate points that you're working with. And then for each of those edge pixels, what you want to do is calculate the distance from that point. So let's say you have an image and then you've calculated all your edges. So let's say you have a few points that represent your edge. So what you want to do is calculate distance rho from that point. So you're going to calculate this distance here. I call d. Sometimes you'll see it as the the variable rho here. So you'll calculate that distance and then you're going to sweep through angles 0 through 180. So we're going to have a bunch of different lines that pass through that point. That's what you'll be doing. And then you want to count how many pixels intersect with that line. So there's going to only be in this picture one line that intersects all these points here. Okay. So you're going to repeat the step for each point in the image, and then you're going to apply some threshold and determine which combination of rho and theta have the highest value, and then that will correspond to potential points that describe the line. So you're going to get an image that looks like this, which is distance by angle. And you're going to see these two bright spots, which correspond to the combination of angle and distances that produces potential lines. So it's like you think of this as like a bin counting, and it'll just count which combination occur the most. Okay, so that's a general idea of the hue line transform. And the idea to get in OpenCV, you're going to see a part where they try to calculate the 2 points on the line. The way that works is you could first describe the distance vector as x cosine theta plus y sine theta, and you can imagine this could be like in the I and in the j direction, for example. And then here you have a vector that describes it, and then d hat is the unit vector. So the idea is you have a d hat vector, and then you have a l hat vector. So the L hat vector is in the direction of the line. So the idea is if two lines are perpendicular, then the dot product is going to be 0. So you'll use that property. So if you expand this out, you'll get Lx cosine plus Ly sine. And by inspection, you could tell that the dot product will be 0 when Lx equals negative sine theta and when Ly equals cosine theta. So that is our direction vector. So we know that L hat is gonna be equal to these values. So if we know the value of L hat, we could calculate one of the points by using D plus a scalar value times L hat, and then the other point is D minus the scalar value times L hat. And K, you just choose some arbitrary big number so that it can span the image. Okay, so without further ado, let's jump into the coding example. Okay, so as usual, let's go ahead and import the modules that we will be using. And we have definition, hue, I call this hue line transform here. So inside of here, let's go ahead and read in our image. And we're going to do some blurring initially because sometimes before the canny edge process, blurring can help remove some noise so we won't get a bunch of nonsense lines that we don't want, which is why we're doing the blurring. And we have a big image, so we'll use a big kernel. And we'll call the canny edge. This will be our canny edge result. cv.canny. We'll pass in our blurred image, and we'll play around with threshold values. The two thresholds to be 50 and 180. So let's go ahead and take a look at what that looks like. So we have our subplot here. We could see our image. And plt.subplots 142. We could do plt.show our blurred image, and then plt.subplots 143 plt.show, and then we could do the canny edge and plt.show. Let's take a look at what we're dealing with. Okay, so you notice that we see some lines here, and if we look at the smooth version, notice here the ground especially, it's a lot smoother, so that way we won't pick up all that noise when we're doing the edge detection. So our goal here is to identify the main line, and we see there's a nice line here that we could extract out. Okay, so here we'll do the main processing for the hue line transform. So here we have our function. We have a distance resolution of 1, so 1 for every pixel. We have an angle resolution we define mp.pi over 180. So increments throughout 180. So not pi over 180. And we have our threshold equals 150. And then our lines equals, call our function here, cv hue lines. And we could pass in our image after canny edge, and pass in our distance resolution, and then we have our angle resolution, and then we pass in our threshold value. So that's our lines function. And here we're going to use a K of 3000. 2000 is actually a little bit too low, so we upped it here. So we have cur line in lines. So here's where the magic happens. So inside of this for loop, what we want to do is we're going to calculate rho and theta and cur line. based on the structure of the array, we had to get the 0th element. You could debug it to see what happens there, but it's just the structure is why we had to do that. And here we have d hat, and we define it as mp dot cosine theta. So that's one value, and then mp dot sine theta, that's our second one. So that's our d hat, and d is rho times d hat, and L hat is going to be very similar. So I'm going to copy paste this. So here we have L hat. The main difference now is you have a negative, and this is sine, and this part is cosine, and that is positive. So our first point P1 equals D plus K times L hat. And then our second point is just going to be minus. So that's our P1 and P2. And we want to convert it to int. We could use P1 equals P1 dot as type and int here. And likewise, we could do P2 as int. So now we could call the line function to plot it. So we have our image, and then we have our P1, 0. We're going to index 0 twice because it's a column vector. And here we're going to have 1, 0. So that's our first point. And then our second point, let's just copy this. So our second point is going to be P2. It's our second point. And then the color that we'll be dealing with is going to be 255, 255, 255, 255. And then the thickness, we could do 10. Okay, so we have our image line, our point here. Okay, let's see if that's good. All right, and now we could plot our final image that shows our line. So plt dot subplot 144 plt dot show, and we can see our image here. So if I go ahead and run this, we should see our line drawn. Okay, so we got our line here. So notice that if we were to have, let's say we skipped this step here and just pass in the image directly, or even if we just play with the threshold value, actually, that might be another way to view this. So if I change the threshold to 50, for instance, and ran the code, we'll see that we get a bunch of lines. Okay, so this may not be what you want. Or it could, depending on what you're doing. But in our case, we just want the dominant line, so we played around the threshold value to get 150, and that's what we wanted. So you can see if I just lower it a little bit, you can see the changes that's made. So even with 139, it identified a few more lines. And notice here that it picked up 2 lines, and that may not be something that we want. Okay, so if you found this video helpful, give a like and subscribe, and I'll see you in the next one. All right, in this video, we're going to talk about the Harris corner detection. So we'll start off by saying what it is, why do we need it, how does it work, and jump right into a coding example. So by the end of this video, we'll see how we can detect some of these corners here on the right. So what is Harris corner detection? It's a method to find corners in an image. So here you can see these are some corners that it has found, and we'll see how we can actually do that in code later on and describe how it works. So why do we need Harris corner detection? It's good for feature detection, and we'll talk about features a lot later on, but essentially features is what lets you distinguish certain uniqueness of an image, and you can also, correlate two different images together based on the similarities of the features. It can also be used for things like calibration, because maybe you want to detect certain points on a grid. So how does the Harris corner detection work? The way it works is that it tries to maximize the equation here by finding the most change in all directions. So you have this function here, and if you imagine if you were to shift it in both the u and v direction, so essentially every direction, and you want to see which one will give the most change, then that will usually correspond to a corner. So you could simplify this equation by writing it out this way. And in practice, most people just look at the x and y gradients, which is the ix and iy. So here we create different images. Here we have a product of ix, x and y, and then x and y again. These two are the same. So the idea is you have these images and you're going to sum up the different windows of those regions. And that will give you your M matrix. And based on the M matrix, we have like a response equation, and that is calculated using this, the determinant of M minus K. This is empirically determined, and it's typically between like 0.04 to 0.06, and the trace. So the determinant is calculated using the product of the eigenvalues, and the trace is the sum of the eigenvalues. So the idea is you have when r is small, when uh, the two eigenvalues are small, then the region is flat. When one is bigger than the other, then it's edge, and then when both are large, then it's a corner. So the idea with eigenvalues is, if you have a distribution that looks like this, then you have like one big eigenvalue and one small eigenvalue. So that's this case. So that typically that would correspond to an edge. And then if it's very small, both eigenvalues are small, then that could be flat. And then if everything is large, then most likely you have some distribution that looks like this. Then that would be corresponding to a corner. Okay, so you can imagine these as being the intensities that you see. So if you plot this out, maybe this is like ix and iy. So you can see there's a lot of change in the x, a lot of change in the y. So you might have like big eigenvalues for both directions, and that will correspond to a corner. So that's the general idea of the Harris corner, and we'll now see how it works in code. Okay, so as usual, let's go ahead and import some of the modules that we will be using. Import cv2 as cv, import matplotlib.py plot as plt, import numpy as np, and then import os. So we're going to call our function Harris corner, and then we have our if name equals main here, and call our Harris corner. Then what this will allow us to do is we'll run our function inside here. We're going to have roots equals os dot get cwd, and then image path equals os dot path dot join. We're going to pass in roots, and then demo images tesla dot jpeg. And we have our image equals cv dot onRead. We're going to pass in the image path, and we're going to have a RGB version cv dot cvt color image, and then we're going to have cv dot color bgr to RGB, and then we have a gray version cv dot cvt color image, and then cv dot color bgr to gray. Okay, so now we have another gray equals, we're gonna do a data type conversion, mp.float 32, and we'll pass in our gray image. So plt.figure, let's go ahead and look at our image. So plt.subplot of 131, and then plt.show, and we'll pass in our grayscale image, cmap of gray, and then plt.show to show the image. So if I go ahead and run this, you can see this is a grayscale image that we're working with. Now we could go ahead and run the Harris corner plt.subplot 132, and then we're going to define a block size of 5, which we'll use for the Harris, and then the Sobel size for the gradient calculation of 3. And k is our value that we could play around with, but we'll start off by using 0.04. And now we could call the Harris using cv.corner Harris, pass in our grayscale image, the block size, and then the k size, and then the k value. Actually, this we call Sobel size. Okay, so that's our Harris, and we do plt dot show and pass in Harris. Now, if I run this, we should see the Harris response. Okay, so notice that it looks like nothing at first, but if you zoom in, you can see there's like bright spots. So these bright spots will correspond to areas that it thinks is a corner. So you could zoom into a Tesla logo here, and you can see that, this is the response that I calculated. And you can see it's like a big blur. You could use things like non-maximal suppression to find the peaks in the region. But this Harris corner method here just gives you the raw response. And we could try to plot the response more clearly on our image by using PLT. We'll make another subplot. But what we're going to do is say the image, and then we're going to do some comparison. So if it's bigger than 5% of the max, so that will kind of pick out some of the key ones. We're going to mark it with this color, red. So now I'm going to do plt.show and then our image. So if I go ahead and run this, we should see our image marked with red where it sees corners. So obviously there's a lot of bad ones, or bad or good depending on your point of view, but at least here in the logo, you can see that these are the corners that it has detected, okay? And if you look back in some of the trees, you can see that it has identified some of these areas as also corners. Okay, so that's the idea of Harris corners, and if you found this video helpful, give a like and subscribe, and I'll see you in the next one. All right, in this video, we're going to talk about SIFT in OpenCV using Python. So we will start off by saying what it is, why do we need it, how does it work, and jump right into a coding example. So by the end of this video, we will see how we could get this image here on the right. So what is SIFT? It stands for Scale Invariant Feature Transform. And it's a method to find features in images. And the idea is the key part is the invariant. It's supposed to be invariant to scale and rotation and things like that to make it more robust. So you can see here on the right is an example of all the features it has found as well as the orientation, which is shown by the line. So why do we need SIFT? We talked about robustness earlier, so it's kind of inherent in the name. And also just in general for feature detection, and feature detection can be used for various purposes such as localization or aligning images together. So how does SIFT work? There's a couple of steps involved. So step one is called the scale space extrema detection, and it all revolves around the idea of finding blobs. So blobs can be found typically with LOG, but DOG is an approximation to LOG that makes it more efficient in real-time computation. So the idea is you will have this is a 2D image, but if you imagine this is 3D, it's like they call it the Mexican hat. But if you were to convolve this image, if a blob is inside this area, then the signal in that area will be amplified, and that's why it's called the blob detector. And the idea is you'll obtain a Gaussian pyramid, and for each pyramid, you will do a different sigma. So like sigma 1, sigma 2, and the difference of the sigmas will give you the difference of Gaussians. And then from there, you'll find features, the ones that stand out, and the extreme points will be potential candidates for your features. Step two is key point localization. So what this means is you want to find where they are, and there's different steps involved. Some of it involves removing low contrast points, and it tries to find a more accurate location by finding the minimum or maximum, which is a derivative when it's set to 0, using the Taylor expansion. And then it wants to reject points with high edge response using the Hessian because typically those are unstable to noise. And you have orientation assignment, so you'll calculate both the magnitude and the angle of the key points, and that will define it some direction that the key point has. And it's just using basic, the inverse tan and square root of the magnet of the x and y components. And you have what's called the key point descriptor. So this is important when you're trying to match things into images. But the idea is you have a key point and then you look at the neighbors. Then you find the direction using the gradient tan inverse to find the gradient, the angles of the different pixels around it, and then you get a distribution plot of okay, how many of the pixels are pointing to the right, how many pointing to this direction, how many pointing up, and so on. And then you get a vector for each feature that has, this distribution. And the final step is the key point matching. So now that we have this vector, you could see which features have the similar distribution of neighbor orientations. And then from there, you could do a nearest neighbor search, and using an L2 distance, you could find which one has the smallest error between the neighbors. And then from there, you could find potential matching candidates. Okay, so let's jump right into a coding example to see how this works. Okay, so as usual, let's go ahead and read in the modules that we will need. So we're going to call def, call this SIFT. And inside of here, we're going to go ahead and read in our image. And now we're going to create a SIFT object using the cv.sift create here. And we could get our key points by using sift.detect, pass in our gray image, and then none for the second argument. And we have image gray equals cv.draw key points, which will draw our key points in our image. And we could pass in key points, our output image gray here, and then this flags is an option to see our orientation and magnitude. So cv dot draw, and then it's called matches flags, and it's gonna be called rich key points. Okay, so that's gonna show us our orientations and all that good stuff. And then we have plt.figure, plt.show, pass in our grayscale image, and then plt.show. So if I go ahead and run this, we should see our image with our features. Okay, so notice that it has detected a lot of features of various sizes. You can see the ground, it got a lot of features, which may be a good thing or bad thing depending on what you're doing. But you can see the trees has a lot of features as well of different sizes. So it's very interesting to see the output. And you can see here there's a giant feature that it has detected. So maybe if you're comparing images of the car in different views, this might be a significant feature to use. Okay, so hopefully you got a good understanding of SIFT and how to run it in OpenCV. So if you found this video helpful, give a like and subscribe, and I'll see you in the next one. All right, in this video, we're going to talk about optical flow in OpenCV using Python. So we will start off by saying what it is, why do we need it, how does it work, and jump right into a coding example. So by the end of this video, we will see how we could track all these points here on the right, and as well as another example that we'll see at the very end. So what is optical flow? Optical flow is used to estimate the motion of objects between two consecutive frames. And we have what's called a dense optical flow, which will look at every pixel inside the image. So that's using this method called Farnaback. And then we have a sparse optical flow, which will use only the features, which we'll see in Lucas Canady. Okay, so why do we need optical flow? It's good for motion analysis, object tracking, gesture recognition, navigation, and so on. So here we're implementing an example of tracking points in this video of me kayaking. So how does optical flow work? So with Lucas Canade, the way it works is you have a pixel intensity, and here we're looking at a function of time. And we're saying that the pixel location and the next pixel location at a new time is about the same. So we can express each pixel with the partial derivatives, which we call ix, iy, it, and the velocities, vx and vy. So from there, you could write a system of equations, as we can see here. So these are all of our points. And then for all of our points, we could set it up into a ax equals b type of matrix. In this case, we're using v for velocities. So you just plug it into your favorite solver, and then you could find out what the velocities are. So that's the general idea. And then for Gunnar Farnabach, the way this works is you approximate the neighboring pixels with a polynomial equation as a function of the displacement. So each point you could predict it as a polynomial equation, and then you could find the coefficients of the polynomial to determine the displacement. So the general form is going to be of this form. So you can see it's a quadratic ax transpose ax. That's typically a quadratic form. So if you expand it out, you'll get some equation. And the idea is, I won't go too much into the details, but the idea is you have equations that describe each point, and you have some displacement d, and you do some rigorous math, and then you find out what the d is. And this is a general idea, but in practice, they have other methods of implementation. Okay, but the general idea is solving a system of equations, and here we're finding the displacements for each point in our image. Okay, so let's jump into the coding example. Okay, so here we have our optical flow program. So here we import the modules that we need, and then we read in the image with the kayaking video that we have. And then what you want to do first is set up your Shitomashi corners parameter, which I talked about in one of my previous videos. And here we have our Lucas Kanade parameters that we will set. So here we have a window size, the max level. So if we look at our Lucas Kanade, right, we have the different things that's new here is the max level, right? So yeah, here we have the max level, which will be like how many levels for the pyramid. And then we have our criteria that we'll use. So this criteria here is similar to the different criteria that we've seen before. And then that is your stopping method if it's based off of the error or the max iteration. And then you have a max iteration you specify, and then also a float for min error. Okay, so your window size is going to be the size that you're going to be searching. And then to see the different points and how they change over time, we're going to use random colors. Okay, so that just makes it easier to see how it's changing over time. And then here we have, we're reading in, we're going to find the features to track now. So we read in our first image, and then we convert it to grayscale. And then we find the good corners using the Shitomashi parameters. And then this will give us all the corners. And from there, we could create a mask based off of our frame. Okay, so we're going to loop through each video frame here. So here we get the frame that we're looking at. And then the next step is we convert it to grayscale. Then we run the algorithm, the calc optical flow PYR LK. So this will calculate your optical flow for a sparse feature set. So this will return, here we have the next points, which I call corners cur, and then the status if it was found or not. And then error we are not using right now. So this will find all the new corners that it found in the next frame or the current frame that we're looking at. Okay, so then if the corners is not none, what we want to do is we have our corners cur. So this tells us the status. So 1 if feature match found between the two images, and then 0 otherwise. So what this tells us is we want to get all the corners that had a match. Okay, so then here we're gonna store our current match and then our previous match into these two. And then we're gonna go through both of them and then see what that is. Okay, so we have a corners current match and the previous match, and then from there, what we want to do is find the x and y coordinates, and then we're gonna draw a line connecting the previous and current coordinates. Okay, so that's what this does. And then each frame we're gonna draw a circle, and then the circle will be the different colors that we have. And then here we add together the things that we drew as well as the previous frame, and then this will be our new image. Okay, so Now that we added everything, we could plot each frame one frame at a time, and then we will update our previous with our current and then repeat the process. So if we go ahead and run this, we'll see um, all these points here are being tracked as we want. So that's all looking pretty good. And you can see all the curvature that's happening is how this pretty much the motion of the camera that you're seeing. And then this blue one here moves a lot because that's the actual kayak that's moving. So let me play that again for those that uh, want to see more detail. So you can see, right, you have all these points here. What you want to pay attention to is this one will have the most movement, or one of the most, because this one is a kayak here. So it's going all over the place. Okay, so this one is our dense optical flow. So what this one will do, let me just comment this one out. So with the dense optical flow, we're going to read in the image as usual, and then we're going to prepare the HSV frame here. So the HSV will do a video capture. So we're going to get the HSV values and then set the last or the middle one here, the 1, which is the second. You have 0, 1, 2. So we're going to set the middle one to 255. And this will just make everything dark essentially. So this here is while true, so we read in the current frame and then we convert our color into grayscale and then we pass it into the Farnaback method. So what this one does, what's new about this is we want to pass in the previous image and then the next image and then the flow. So flow here is set as none. We're just using the output here. And then we have the levels, this number of pyramids that we have, which we pass in here as 3. And then our window size, the averaging window, so it does a little bit of blurring for us. And then the number of iterations we have is 3, and then poly-n is the size of our pixel neighborhood, so that you typically want to choose 5 or 7. And then the poly sigma here, we use 1.2, so you could play around with these different values, but typically n equals 5, you could use that, or 1.5. So I played around with it, and you could kind of see how much that changes. And then the flags, you have two options. You have use initial flow or then the cornerback Gaussian. So that's the one we're using. So this one uses a Gaussian window instead of a box filter. So Gaussian window will have a little bit more better transition smoothing than a box filter. So then from there, we take the flow. The flow we see here is m by n by 3 image. So we will take the magnitude and angle based off of the first 2 channels of the flow image, and then use a cart to polar to get our magnitude and angle. Okay, so then from there, we're gonna convert our angle into degrees. That's why we're multiplying it by 180. And then we are going to normalize the magnitude to 0 and 255. And then we convert it back to BGR here, and then we plot our image. Okay, so if we run this program, we will see the points. This is the dense optical flow, as we said. So if you look here, these are all the points that's changing over time. And then some of the background, because it's further away, it's not changing as much. That's why you see black in those areas. Okay, so if you look closely, you could kind of see the kayak paddle here moving. That's the main part with the most motion. So you can see those colors are a little bit different from the rest. Okay, so if you found this video helpful, give a like and subscribe, and I'll see you in the next one. Alright, in this video, we're going to talk about camera calibration in OpenCV using Python. So we will start off by saying what it is, why do we need it, how does it work, and jump right into the coding example. So by the end of this video, we could see how we could take a distorted image here and then undistort the image. Okay, so what is camera calibration? So camera calibration is used to obtain the camera parameters. So we have 2 types, what's called intrinsics and extrinsics. So for the intrinsics, what you have is the focal length, and then you have the principal point, which is the center of your image, which we call the CX and CY. And then you have the distortion parameters, which we call K1, K2, P1, P2, and K3. Okay, so you have the extrinsics. So for this one, you have the rotation matrix, typically is a 3x3, but OpenCV has a 3x1 implementation. And then you have a translation, which is a 3x1 matrix. Okay, so what is camera calibration? So to really understand this, you have to know the camera model. So for the camera model, you typically have a camera center, and then this here, what you have is called the image plane, and then this point out here is your world point. So for like a camera calibration, the idea is we want to find these parameters so that if we were to project this point onto the image plane, how do we project it correctly? So all of these parameters we need to find needs to be accurately determined. Okay, so the general equation is here. You have a little x equals big P times big X. So this big X is typically going to be your world point. So you have a x, y, and z, and then this one here is just for a filler because of the dimension of this camera matrix here. And then this camera matrix you could see here is a 3x4. Sometimes you'll see it as a different size if they were to like truncate part of it off. That's why you might see this sometimes as like a 3x3, but same idea for here. So here you get the image point, which is our little x. So this is the actual points on our image. Okay. So here, what is camera calibration? So if we break up that matrix, right, what you want to see is the P matrix that we looked at right here can really be broken down into two matrices. So here we have our intrinsics matrix. So this is the part that looks like a 3x3. And what this tells us is the focal length and then the px and py. Sometimes you'll see it as cx, cy, depending on where you're from. And then here is the extrinsic. So this is your rotation matrix, and this is your translation vector. So that's what this is down here. And then for the distortion, you have the different coefficients. You have K1, K2, P1, P2, K3. And how that all comes in is if you were to map your points from your original points, you have different mapping based off of what these coefficients are. So this example down here is what's called a barrel distortion. So depending on what the distortion coefficients are, you'll have a different mapping based off of these equations. And you have what's called the radial and tangential. So you'll have different distortion factors based off of which direction you're looking at. Okay, so why do we need camera calibration? So camera calibration is typically good for applications of like AR, SLAM, 3D reconstruction, or just for having an undistorted image. Okay, so how does camera calibration work? So first off, as you've seen in a lot of cases, people take chessboard images, so that's used for calibration. And what we do is we find all the corners inside our chessboard. So we don't find the outer ones, just the inner ones. So we find all the inner corners, and then we do some process to find the best location where those corners are. After you find all the corners, what you can do is set up this matrix. So we looked at the projection matrix. So here we're looking at mapping between our world points and our image points. So we take that and then we could parameterize it here into this way. So we could make each column written in this way. And then here we have the different parts of our rotation and translation. So the idea is you get a system of equation and you move it to one side, so then you get the form of like ax equal to 0. You wanted to get your equations into this form, and then you essentially just solve for your h. And then we also make some assumption if typically you have like x, y, z, but if z is on an image plane, we could say that the z value is 0. So there's some assumptions that we do. So after you set up your system of equations, you could use a solver to find out what the actual parameters are. Okay, so let's jump right into the coding. Okay, so here we have our camera calibration program. So we're going to import the modules that we need here. And then we have a function here we have called calibrate. So the first function we're going to run is called run calibration. So run calibration will call calibrate and we'll set show pics to true. Okay, so what does this calibrate function do? So this calibrate function, what it does, okay, so what this function does is you can see right here, we read in the image, and then we get our calibration directory, and then we'll get all of our images inside our directory. So we first initialize the number of rows and columns of our chessboard. So this is very important. You want to make sure that you counted the number of corners correctly. And then you set up a termination criteria. So here are termination criteria. We could do a combination of the two. So this is going to be a tuple of 3 values. And then, so here we have the termination criteria, which passes into the corner subpicks. So if we look at the corner subpicks, we have this criteria here. So these are the criteria that we look at, the 3 tuple with the enum, the stopping conditions for the error, and the max iteration. So here we're gonna do a combination of the two. And then what we want to do here is create some world points. Okay, so the world points is what this does is it'll help us. We're gonna use these points to project it on later, but then for now we're just creating like numbers from like 1 to the number of rows and columns as placeholders for the world points. Okay, so we're gonna create 2 empty lists here to store our points as we calibrate our camera. So here to find the corners, we go through all of our images, and we're gonna read in the image, convert it to grayscale, and then we're gonna call the find corners, find chessboard corners function here. So what this does is it takes in your image, which we're doing grayscale, and then we have a pattern size, which we have n rows by n column, and then the flags, which we're not using. And then what this will return is your return value of the corner was found, and then your corners. Your corners here, which is a n by 1 by 2 numpy array of your x and y coordinates. Okay, so this should be 2 because we're using grayscale. But anyway, so here you have, if we found the corners, what we want to do is append it to the list of all our world points. And then we want to pass it into the corner subpicks. So this corner subpicks function here, what this does is it's going to find a more accurate location of your corners. Okay, so here we pass in our image grayscale, the corners that we found, the window size, which you're using as 11 by 11, and the 0 zone, that's the region in the search that is not used to avoid singularity. So -1 means none, so we're not using that. And then we have our termination criteria that we just talked about. So after that, we append all of our corners that we find, and then we're gonna plot it out here if we say show pics. So here we have our draw chessboard corner. So from here we pass in our image, our pattern size, our corners, and then if the corners were found, and then that will modify our image with the corners. Okay, and then the final step is the calibrate camera. So what this function will do is do the actual calibration. So it's going to help us find the intrinsics and extrinsics. So we pass in the world points list, the image points list. So these will be a size of npick list of n by 3 arrays. And same for the image points, can be an npick list of n by 1 by 2 array. And then the rest is going to be the image size. Here is going to be a tuple. And then for some of the stuff, we're going to set as none because we're not using. Okay. And then the return value, you have a reprojection error, which is a float. You have a camera matrix, which we'll need is a 3 by 3 matrix. Your distortion coefficient, which is a 1 by 5. And then your RVEC and TVEC will be tuples of 3 by 1 for all the individual cases. Okay. So here we're going to print out the camera matrix and then the reprojection error to take a look. And then this logic here is going to save our calibration parameters, which we will use in our later video. So we just want to prevent running 2 programs, so that's why we're saving it. So if we go ahead and run this, we could see our calibration happening. So each of our pictures, we're running it and then finding all the corners. And you can see that all of these are nicely done and all the corners were found. So if you see here, we print out our calibration matrix, right? So, and we have a reprojection error in pixels of 0.1687, which is pretty good. And you can see that we have our F value, which is the same here. And then this is our X and Y. So those all look pretty good. And some things to make note of when you're calibrating, I would say make sure I mentioned the corners. You want to make sure to count the number of corners. You typically need at least 10 images, and the images should be taken in different planes. So you kind of want to rotate and pivot it so they're not on the same plane. Otherwise, you'll get a degenerate case, which your solver will not be happy. And then you want to make sure your entire chessboard is inside the image. Okay, so next up, we're gonna try to remove the distortion. So we have a function here called remove distortion. So what this does here is we're gonna read in our picture. We have a special picture here that we're gonna try to undistort. And then what we have here is we're getting the height and width of our image. And then we have our function get optimal new camera matrix. So that's a function that we're using. And what this does is it computes the new camera matrix to account for distortion. Okay, so based off of the distortion coefficients that we have, we could figure that out. So what this takes in is going to be the image size, alpha, and the new image size. So for the sizes, it's going to be the same. That's why we're passing in width and height. And then this alpha here, what this means is a scaling between 0 and 1. So for alpha of 0, it means that the rectified image zoomed and shifted so only valid pixels are visible. And then for alpha 1, all the pixels from the original image are retained in the rectified image. So we're going to go ahead and use the 1 option here to, to retain all the pixels. Okay, so here we have a undistort function. So for the undistort, what this does is, so for the undistort function, what this does here is you have your source, which is your image. We're calling this image here. And this is going to be a NumPy array. And then we have a camera matrix. It's going to be a 3 by 3. And then our distortion, the distortion coefficients. And the DST is like the destination. We're not using that, but because we're using it as an output here. So this is image undistorted. Okay, so that's what this function is. And then what we're going to do is draw the line. So we're going to draw the line to visualize how much distortion is happening. And then we're going to draw the same set of line in this undistorted image and compare the results. So if I go ahead and run this, we can see that we have a picture of a chocolate here, right? And it's very subtle, but if I zoom in here, you can see that if I draw a straight line, there's a little bit of black that you're seeing. So you could tell that that image, there's a little bit of curvature happening. And then now that after distortion, it pretty much matches the edge of that part of the chocolate. Okay, so you can see part of the distortion has been removed. Okay, so if you found this video helpful, give a like and subscribe, and I'll see you in the next one. All right, in this video, we're going to talk about pose estimation in OpenCV using Python. So we will start off by saying what it is, why do we need it, how does it work, and jump right into a coding example. So by the end of this video, we will see how we could draw this cube here on the right on top of our calibration images. So what is pose estimation? The idea is finding both position and orientation of an object in a video or image or video. So why do we need pose estimation? So we have augmented reality, you have activity recognition, film and animation, and many other examples. So how does pose estimation work? The idea is you have world points are projected onto the image plane. So here are your world points and it gets projected onto your image plane. And we are trying to find the position and orientation that minimizes the reprojection error. So you may have the true point here, and then you have like a projected point here, and there could be some error, and you might have errors between all the points, and we're trying to minimize what that error is. Okay, so the idea is you have your image points and you have your world points, and you have some transforms that relate the two. You have your intrinsics, you have additional matrix here, and then you have your rotation and translation, which capture your extrinsics. So all of this combined will give you your projection matrix that brings your world points to your image points. And then from there, you could rewrite it into a more compact expression here, as you see down below. So the idea is we want to estimate in OpenCV, we call it as RVEC and TVEC, and then those are the actual parameters that we're trying to find. Okay, so there's typically different solvers that are out there. You have um, here we have the solve PNP iterative. So this is the default one that we'll use, but then there's some other ones too, which we won't go into too much detail with. But for the iterative one, you have the what's called the Levenberg Marquardt. And what this does is it takes like the Jacobian and does like a Newton type of method of minimization error. So if you have like a function here, and then you're essentially trying to get lower and lower and lower until you find the minimum. So this is like a two-dimensional case, but you expand this to a multi-dimensional case using what's called the Jacobian. But essentially, it comes down to minimization error by looking at the gradient at each time step. So that's the general idea. And then you also have like DLT methods, which tries to solve like least squares directly. Some methods uses like SVD and so on. But you can see part two, you have some other different methods that you can explore. But usually the default one works fine. So that's the one we will use in our example. So let's jump right to it. Okay, so here is our post estimation script. We import some of the modules that we need, and we're going to declare an enum of two types because we're going to be drawing axes and cube later on. So we made an enum for that. And we have a draw axis function here, which we'll use, and I'll explain in a bit. And same with the draw cube, which I'll explain later. But the main program we're running is called the post estimation function. So what this function does is it's going to take the draw option based on what we're drawing. And what we want to do first is retrieve the camera calibration that we obtained in our previous video, pull it out from the script, the calibration.mpz file, and then read in the values and store it as the cam matrix and distortion coefficient variables. So after we do that, what we want to do is get all the paths for our images. So I think this might make more sense if I say obtain image paths here. So we're going to get all the paths for the images. And then what we want to do is set up our termination criteria, which we talked about before. So here we have the EPS and iteration. So that's the error and number of iteration count. And then same here is if we take a look at this, we set up to have the number of our error and iterations that we set. So we take our world points here, and from our world points, what we do is we assume some location in the world space, and then this step here is we're going to try to reshape that into an array, into the structure that's going to work for our functions later on. Okay, so what we want to do here is define some axis points. It's just arbitrary points in the world space. And then we want to find cube corners, which are more points, the 8 points of the cube. And those will be used to project from the world points into the image plane later on. So the steps here is similar to a camera calibration. We find the corners. So we read in the image, convert it to grayscale, pass it into the find chessboard corners. We find the corners. Okay, so after we find the corners, call corners org. After we find that, we refine it using the corner subpix function, which we talked about in the camera calibration. And then the new function here is called the solve PNP. Okay, so the solve PNP function, what this does is it finds the rotation and translation vectors, which is here, and we'll use that to do some of our projection later on. So what this takes in is the world points. Here is called object points. So that's going to be an n by 3 array. You have your corners refined, which is a m by n numpy array. Your camera matrix, which is going to be a 3 by 3. And then your distortion coefficients, which is a 1 by 5. So based off of our drawing options, first off, we're using the axis. So we have our project points function. So what this one does is it'll take in our object points, which here we're calling axes. You have your RVEC and TVEC, and then you pass in the camera matrix and your distortion coefficients. And then what this will return is your image points, which will be an m by n array, and then the Jacobian, which we're not using. So we call the draw axis function that we've defined up on top. So what this does is it'll take your image, your corners, and your image points, and then it's going to draw the lines onto the image. And one thing to note is we need to do some conversion to make sure that all the points are integers. So that's what we're doing. And then we do the RGB for the different axes, which is what these different color codes are for. So if I go ahead and run this program, we could see our axes being drawn. So if I run this, you see we have our axes drawing for each of the image, for a calibration image that you have. So you can see that my camera is rotating and the axes are adjusting accordingly. So that tells us that our calibration is looking pretty good. Okay, so now if I take a look at our next step, so here is our cube implementation. So the only difference, everything else is the same. We have a different option here for draw cube. So we're going to project it, but now with our draw cube function, it's a little bit different. We're going to read in our image points. We're going to create a contour, which is going to be the green plane. And then for each of the corners on our cube, we're going to connect the dots and draw the borders of our cube. Okay, so if I go ahead and run this, we will see our cube being drawn with the plane where it's on the chessboard. Okay, so you can see all the images is adjusting accordingly to the translation orientation, just like we want. Okay, so if you found this video helpful, give a like and subscribe, and I'll see you in the next one. All right, in this video, we're going to talk about depth maps in OpenCV using Python for stereo vision. So we're going to start off by saying what it is, why do we need it, how does it work, and jump right into a coding example. So by the end of this video, we will see how we can get two stereo images and get the depth map as we can see here up on top. So what is depth map? So sometimes you'll hear it called disparity map, and they mean the same thing. But what this describes is the distance between each pixel between matching points from two stereo images. So if we actually look at each um, value here, this will tell us the disparity for the individual pixels, which will tell us that for this point in both images, that is the distance between the two pixels. So the disparity equation can be defined by x minus x prime, or the left and right image. And this is equal based off of some similar triangle geometry. B, your baseline, which is the distance between your two cameras, times f divided by z, which is the z distance to your world point. And you can see this figure here that describes that geometry. So why do we need depth map? There's different things you might need it for, such as 3D reconstruction. You could take a depth map and convert it to a point cloud. You could do things with AR and things with depth estimation if you want to measure things for certain applications. So how does depth map work? The idea is you do what's called a block matching. So you'll take a window here. I exaggerated the window, but you could have two windows, and you may be searching along some epipolar line, for example. So you may find a search, keep sliding the window along this line, and then you could compute different metrics such as the sum of absolute difference, sum of squared differences, or the normalized cross correlation. And what you would do is find which one gives the best response, and that would be your potential matching point, which is very similar to the template matching video that I talked about. You could go check that out, but it's a similar idea. So to make it a little bit better, there's another method which we call the semi-global matching. So it's also called SGM. Sometimes you'll call it SGBM, but most commonly you'll see it as SGM. That's the main thing. So the idea of that is it tries to minimize the energy function. Okay, so the energy function is defined here as a sum of C. So C right here is going to be the matching cost that we just talked about, and it's going to be a function of your pixel. And then you have two different sums. So you have a penalty based off of your disparity values. So if your disparity is equal to 1, you get penalized by something. And if your disparity is greater than 1, then you get penalized by P2. So this penalization factor controls the smoothness of your disparity map. And then in practice, to really get this energy or cost function, what we actually do is we will take 16 paths from all directions, and then we're going to try to find the path that produces the minimum cost. So you will have an equation that looks like this. So essentially, you do this for every pixel inside your image, and you will find you'll find a global minimum, which will represent your disparity match. Okay, so there's a lot of math that goes behind this, but this is just a high level overview of what's happening. Okay, so let's jump right into the coding. Okay, so here we have a function. We're gonna do our demo view picks. So inside our demo view picks, we're gonna call our depth map. Depth map, what this init function does is gonna get the root path and then get the left and right path and read in the left and right images from the path and store the images as grayscale. Then from here, if the show image option is true, we're gonna go ahead and plot it. So let's go ahead and run this. Okay, so you can see our images here is showing up. So this is the left and right image of our motorcycle. Okay, so for our next function, what we're gonna do is we're gonna there's two main functions we're gonna test out. One is the block matching. So here the block matching we're gonna compute. It's called our compute depth map BM. So what this function does is we define some n disparity factor. So what we do here is we're gonna call our stereo BM dot create. So what this does is it creates a stereo BM object so that later we could compute the disparity map. So what this takes as an input is a number of disparities. So usually the number of disparities is going to be a multiple of 16. So that's why we multiply it by some factor, and we could play around with this factor 6 to see which gives better results. And then we have a block size, which by default is 21, but we could play around with it. It should just be odd and more than 1. And then here we have the disparity. So stereo.compute is going to actually return the disparity. So this is going to be an m by n numpy array, which is our disparity. And then we pass in the left and right image, which is a m by n numpy array as well. Okay, so if I go ahead and run this, we should see our disparity map. Okay, so you can see here that it's all black. From just by looking at this, I know it's not good. And typically what you expect from a good disparity map is you want to see there's a nice gradient from forward to back. And typically you would have the points that's further away would have less disparity, and the points closer away would have more disparity, because you can imagine points further away tend to look like they're at the same location, whereas points closer away, there's more movement between the points if it's closer to the camera. And you can see if I hover over this, you see some negative 16 values down at the bottom in your browser. So if I move this, you can see a little bit better. You can see if you focus down here, you can see the actual values that these pixels are. You can see this negative 16, so that's not very good. And then back here, you can see some values as like 800. So I would say this is not too good. But if I play with a SGBM, it's going to give us better results, which we'll see in a bit. But let's go ahead and adjust this factor here to see what happens. So if I make this 12, let's see what happens. So you can see that some of the black part disappears. The wheel part becomes whiter, so that's a good sign. But still, I would say overall, this is not a very good disparity map. So we're going to go ahead and take a look at our other function. So our other function uses the SGM. In OpenCV, they call it SGBM. So this has a lot more parameters we could play with. So we're going to call the next function in the next step here. So here, what this does is we have window size, which we declare here, and then we have a min disparity. We have a n disparity factor, so we could play around with that. We have a number of disparity, which we'll define as 16 times the n disparity factor minus the minimum. So when we create our SGBM object, we could pass in all of these parameters. We have the min disparity, the number disparity, the block size, which is our window size, our P1, P2, which is our penalty factors, and the heuristics. These are just some values that people have found to be good, so we're going to leave that. Typically, tuning these are pretty hard, so I'm not going to tune it in this demo here. What I do find is that tuning this value changes it a lot, so we'll play around with that. So here we have some max difference. It takes it as an int. We're going to set that to 1. We have a uniqueness ratio. here. So what this does is a margin in percentage by which the best computed cost value should win the second best value. That I played around to be 15, speckle window size of 0, the speckle range. So this is just controlling max size of the smooth disparity region. So based off of the how much noise there is, you could play around with that. And then the speckle range, which is the maximum disparity variation within the specified window. And then you have the pre-filtered cap. So that's set at 63. And then here we have pre-filter cap truncates disparity value falling outside of this range. And then the mode that we're going to be using, there's a couple of different options. So the mode we have here we have the CV.stereo SGBM mode SGBM. And then you have the mode HH, mode the three-way, HH4, and the quarter. So there's just kind of some optimization methods there's like a trade-off between how fast and how good the results are. So right here we're playing with the three-way method. So let's go ahead and choose something like 7 for now and see how that looks. So if I go ahead and run this, we'll see what that looks like. So you can see that this is the results here. You can see it's very fuzzy. It's not smooth like I prefer. So you know that this is not a very good depth map. And if I go ahead and change this to 14, which I found to be pretty good, and if I run it, so because there's more disparity, so it'll take longer, but you can see this is more or less something I would expect. So you can see that these values here in the back are darker, the values in the front are brighter, and it's has a decent range from forward to back. So I would say this is a pretty decent depth map. And you can see if I hover over it, it's gonna display the values for the disparity. So again, if you pay attention to the corner down here, you can see the disparity values here. It's like 176. In the back, it's like 70s. The darker region is like 40s and so on. Okay, so if you found this video helpful, give a like and subscribe, and I'll see you in the next one.